All right, so let's do this. All right, sorry if that's in your way, but too bad. All right. So, here we are with the multiple choice of the same test, and again, it's all about parallels. Okay? So let's start. Let's be crazy and start in order.
Oh my God.
Yeah, oh my Buddha. Okay. Now, here we go with the first question. According to the information in the table above, a 1 gram sample of which of the following contains the greatest mass of oxygen? Gosh, I've seen this before. This has been a question that has popped up where they want you to do a percent by mass, but they don't want you to spend any time, okay? So if I'm trying to find which one has the greatest mass of oxygen, which is the same thing as saying the highest percent by mass, they made your life easier by giving you the molar mass. All of these have 1 oxygen. So if you minus 16, if they all had the same what? 16 in them, right? I go to oxygen, atomic mass 16. Okay, so the difference in the mass is the difference in the what? Element it's bonded to. So you must say to yourself, okay, then who has the greatest mass, okay, percent of oxygen, okay, then I'm going to think about who is the least massive element that it's bonded to that would give me the greatest percent, right? Percent is part over total times 100, okay? So if I've got a what? Smaller total, okay, all right, then I'm going to have a greater percentage if the 16 is above, right? It's going to be 16 over a smaller total, right? For those that don't get what I'm talking about, part over total times 100. So my friends in chemistry, if I've got a smaller total, okay, they all have the same amount of oxygen, so this would be 16 over small total would give me the greatest percent by mass. And that's why B is the answer, because of all the choices, it's going to have the smallest what? Atomic mass, or at least mass of the element. There's 2 potassium, each one's 39, each one of calcium is 40, magnesium's 24, each sodium's 23. So this is the least massive of the 3, which gives you the greatest percent by mass. I've seen this before. Going over these multiple choices, I've seen this before. So it's kind of a question you want to be able to handle. Okay, number 2. Please stop me if that's not good enough in explaining it. Okay, and you should be starting to see some parallels. Okay, I want to identify a white crystalline solid. All right, now it melts at 320. Okay, does not conduct electricity as a solid. All right, and I'm just being crazy because it's bothering the heck out of me. I'm being OCD here. Okay. All right. Can't look at a tilted video. All right. Even though I'm tilted. All right. Now, 320. Here's the key to the entire thing. It does not conduct electricity as a solid, but does as an aqueous solution. So this is screaming to me what? Yeah, it's an electrolyte. It's free ions, which, by the way, is what ionic compounds are. Okay, now who has free ions? Ionic compounds, acids, because they break apart into what? H pluses and bases. How low can you go? Okay, so this is a non-electrolyte. It's what? Covalent and covalent. This is a molecular compound. This silicon dioxide is a network solid. Okay, it's a non-metal bonded, well, it's a metalloid bound to a non-metal that keeps going. It's sand. Okay, copper conducts electricity in what? As a solid and aqueous, because it has what? It has free electrons that can move. They have mobile electrons. So B is the answer. This is an electrolyte, which can be either an ionic compound, an acid, or base. And why do I know? It breaks apart into Na plus and OH minus. Those are free ions. Electrolytes do not conduct in the solid. Why doesn't this conduct in the solid? Because this makes a what? A crystal lattice of ions, and the ions are not free to move in this crystal lattice like ionic compounds. Number 3. Which of the following correctly identifies which has the higher first ionization energy? Okay. What is ionization energy? It's coming up a lot. We spoke about it a lot. It's the energy required to remove an electron. So the more stable you are, or the more tightly bound an electron is, the higher. So you've got chlorine versus argon. Now chlorine and argon, okay, are in the same group 3. So what we have is we have sulfur, we have chlorine, and we have argon, okay, in the same third row in the periodic table, okay? So let me just do this. So on the periodic table, they're in the same row. N equals 3, which indexes size. But as we go across the periodic table, and let's just kind of see that up close and personal. So let's go see that in your reference table. So touch is not on. Oh, touch is off. Okay, touch is on. So let's get bigger and personal here. Maybe. And we see maybe to the right at some point. Okay, so we see these guys, and look at the atomic mass. Look at the atomic mass increases, but look at the atomic number. Why is it steadily increasing? Because there's more what? Protons. The reason why atoms get smaller as they go across is because they're tightly bound. Because the nuclear charge, the charge in the nucleus, or as we've been saying all year, the effective nuclear charge increases. This is important. This could be a part 2 question where they say explain. They could ask you in part 2, explain why argon has a higher first ionization. And in fact, these guys, the noble gases, have the what? Highest ionization energy. Incorrectly, people say, well, they're the most stable. And I know why people say that, because they have the what? Most stable electron configuration. But the real reason they have the highest ionization energy, in their rows, they have the greatest number of what? Protons, correct. And that's why that answer, okay, is going to be argon, because it's completely filled valence shell. No, because it has a higher effective nuclear charge, which means greater number of protons. I can see why people would pick C. It's a great distractor, okay? Again, everything I'm doing here is grounds for what? Part 2. Okay, here we go with a precipitation reaction. What is the delta H that's positive screaming to you right now? Where does the heat belong? This positive delta H means the entire reaction is endo or exo? Endo. So I have 162 kilojoules per mole. I'm going to put that right in my reaction to remind myself the heat goes here. It's endothermic. Okay? And I may not need it, but I'm going to put it there. Here we go with a rigid sealed container again of a solid. Okay? And it's in equilibrium with the solid and the gas, as represented by the equation above. Which of the following changes will increase the amount of barium solid in the vessel? Okay? So which of the following will increase the amount? So what are they really saying? If I'm going to increase the amount of solid barium sulfate, which way is going to be more spontaneous? To the left or to the right? To the left, to the left. Beyonce, come on now. Okay, it's going to go to the left. If I'm going to make more barium sulfate, that means the reaction shifts to the left. I don't like that word. I'd rather you say it's more spontaneous in the reverse, but they would accept both, right? Delta G is going to be more negative in the reverse if I'm going to increase that. So now what is going to do that? So this, my friends, is a Le Chatelier's question. And when you're doing a Le Chatelier's question, I really would ask you to do it this way, because it gets easy question to get right, easy one to get wrong. Here's what I do. Okay, maybe. I write myself a little chart. I put my stress here. I put my response here. The response is what the reaction does to do what? Regain equilibrium. Party people, as I've been teaching you all year, reactions want to move toward what? K. If my Q is what? Greater than K, I'm going to move backwards to get to equilibrium. If my Q is less than K, I'm going to move forward. This is Le Chatelier's principle. So the response of a reaction is either going to shift to more what? Reactants because the Q is greater, or it's going to shift to the right if the Q is smaller. Did I make a mistake? Okay. I've been known to do that. I usually correct my errors. So, the response is tied to the shifting because of what I explained. So which is the font? Well, look, if I remove a small amount of O2, that's the stress. That's what we do. If I decrease O2, that means I'm going to increase O2 by what? By shifting or making it more spontaneous. How would I increase O2? That means the reaction would have to what? Go in the forward direction more spontaneously, and this would increase. That can't be the answer. Look at the other. Removing barium sulfate. By the way, this is important. Put a circle around this one. This is not the answer. Can anyone tell me why? Removing a small amount of barium sulfate. Now, people would say, Mr. Grodsky, I'm just following what you say. If I remove barium oxide, I should say, okay, don't I want to increase barium oxide? And therefore, that's the answer. And this is a strong no. Because what is this really about? It's about Q versus K, isn't it? And what's a Q or a K formula based upon? Q or a K. It's based upon products over what? Reactants. Coefficients become exponents. And who doesn't apply? Solids and liquids. Look at that. That's a solid. They're going to ask you in part 2, in my opinion, or in multiple choice, why changing barium sulfate will have no effect. I believe they're going to ask you that, feel like that, because that's something they haven't seen in the last 3 tests. And you would say it has absolutely no effect because it's not. It's not a what? Solid or a pure liquid. It has no effect on the equilibrium or the Q. A Q and a K is based upon what? Aqueous gases or what? Okay? Now, of course, in this question, as I incorrectly did, I can see now, they were talking about what? Barium oxide, correct? But that wouldn't be the answer either because it's also a what? Solid. What's the K here? K is equal to just what? Products, and that's it. There's no reactants, right? That's it. That's the KAQ with this, isn't it? So both of these are not in that expression. What would be Q equal to? The same thing, not at equilibrium, correct? Okay, so this will never be an answer. Neither would barium oxide, even though I thought it said. How about, look at C. How is C the same as B? Please, answer this. How is choice C the same as B? Is helium in the equation at all? Because people would say, oh, Mr. Grodsky, you're going to increase the pressure. It's got to be the pressure of one of the what? Elements in your K. So people might say, oh, increasing helium is going to increase the pressure. Increasing pressure will what? Favor the lower pressure, so it would shift that way. A lot of people pick helium because they think by adding helium, you're doing what? Look at this. This is a good review. Increasing the pressure. What would be the response? Decrease the pressure. And when you deal with pressure, you learned last year, you count what? Moles of gas. There's 0 moles of gas on this side. There's what? 1 mole of gas. So if we're going to decrease the pressure, would it shift to the left? The answer is yes, but here's our problem. Is helium anywhere in our equation? Then it would have absolutely no effect. It has to be in the KAQ expression as an aqueous and or a gas. You will see this. It's popping up. It's popping up multiple times. That's a parallel I see. So guess what? That's why C is not an answer. So people would have picked C, a lot of them. That's a smart way to get it wrong. I get it. But here it is, lowering the temperature. The key to the entire problem is realizing that the temperature is really on this side. And if you want to use my little chart, what is the stress? The stress is that we're going to lower the temperature. The reaction is going to shift to increase the temperature. How does it do that? It favors the what? Exothermic reaction, right? Which is the reverse. Which means it'll shift to the left like Beyonce, and we would make more barium sulfate. Now, I have to say this because it's important. Reactions don't really shift with temperature. What do they really do? Right, they become more spontaneous in a certain direction because the what? The equilibrium constant changes. I want you to understand this. Even though we can get this answer right using the basics of that, but listen, if the temperature is endothermic, what happened to this K? It shifted where? It got smaller, yes? So if it got smaller, then what was in this area is now bigger than what? K, and the reaction shifts to the left. Reactions don't shift in temperature, they make a brand new equilibrium constant. And if I know the energies on the reactant side endothermic, I know that the equilibrium is going to shift to get smaller. Okay? Or, just if you have to memorize anything, we always favor the exothermic reaction, which is the reverse in this case, when you decrease the temperature. I don't care how you do it. Okay? So this is a question a lot of people got wrong for many different reasons. You will see pieces of this somewhere. That's what this is about. Okay? Number 5. Is that on top or the bottom? I think I wiped that out. Yeah. Okay. Been known to just skip problems. I wiped them out. Okay. Wipe out. All right. We okay? Everyone's good? Any questions? Okay. Put the checkbooks away. I can't help you. Okay. Which of the following best explains why the value of delta H of 0 for the dissolving of calcium fluoride is positive? It's an entirely different reaction. This is a great little reaction or question that's going to pop up in part 2. They want to know when calcium fluoride dissolves in water, so I put a little H2O on top of here, but you didn't have to. They're not asking for this, but I'm doing this so you can see, okay, it becomes this. Calcium plus 2 plus 2, so this is happening in water. Now this is solid, and this is aqueous. Okay, and this could be a what? A net ion reaction they ask you to do. The question is, why is delta H positive in something called the dissolution? We've been hearing this word pop up, haven't we? What does dissolution mean? Dissolve in water. So that's something we've been seeing a lot in a lot of these tests. They didn't say it, but again, they could have. Now, why is it positive? Think about it. Let's write a what? Let's get rid of this stuff. Let's write a potential energy curve to understand this. If it's endothermic, we start low and we go high. Okay, now what is low? The low is the reactants. The reactants are the solid salt. And the products are the ions. Now when I do this, I can now see what's going on. The delta H, which is the difference of where I start and when I finish, went up. It's a positive value. We just made ions that are more what? Stable or unstable compared to the solid? Unstable. If you've got high energy, this has got a lot more energy as ions than it does as a solid. So we know that the ions are unstable. So somehow in this process, as we try to keep ourselves from falling over, okay, okay, the ions became more unstable. Now why would they be more unstable? Either for 2 reasons. The water that wants to what? Attract them must have weak attractions compared to the what? Attractions between the salt. What's the charge of calcium? What's the charge of calcium? Plus 2. Hello. What's the coulombic attraction of that? And F, isn't F a pretty small element? Now it does get bigger when it gains an electron, but still it starts out pretty small. So there's going to be a high attraction. So the answer to this question, if you look at the 2 choices, CF is insoluble in water. Okay, that doesn't tell you anything about the delta H. Dissolving in water, that could be exo or endo, so that makes no sense. The clear reason is that the ions are unstable, or the product is the reactant is more stable. So the ions have very strong ion-ion attractions in the crystal. What this is saying is that in the solid, it's more stable. And if you're more stable, you're lower energy. And that's the answer. This have very strong ion dipole attractions. That would be with water. If these are stronger, then these are more stable, or it'd be exothermic. So the answer is C. Okay? I'm spending a lot of time in these questions because I really believe that these, understanding of them, is something you could see as an explanation in part 2. Yes? Okay? Why would it not be A? Okay. Which of the following helps explain why the value? Okay. So, if there is a delta H, to begin with, it must mean that there was a reaction. So if it's totally insoluble, there wouldn't be a reaction and no delta H. But don't you know that all things are somewhat soluble? So it's not the best answer. I see what you're saying, that the solid is so strongly attracted to itself, it wouldn't go with the water. But there is going to be some amount of solubility. Okay? So it's not that's an intelligent wrong answer. Okay? Gets you nowhere, but I can see why you would say that. Okay, moving forward. Please stop me with those kind of questions. And if you feel like this is the waste of your time, raise your hand, we'll do something else. We're fine with this? Okay, fine. Number 6. This is a question from Regents Chemistry land. Ideal gases, like the ideal student. What 4 things have to happen for the ideal student? Well, they go fast. They have a big backpack. They bang around into people. Okay? They say, excuse me. They're not going to say, excuse me, just take off. So the ideal student is fast. Because they want to get to the printer to get the worksheets, they go in what? Straight line motion. They want to get back to the what? Seat to stare at the teacher, not miss anything. Straight line motion. That's 1. 2, when they bump into people because they're in a race to get to the what? Class? Their collisions, okay, are elastic. That means they bounce off people. They don't stop to talk with them and say, I'm sorry. They bounce off. Gotta get to class. Okay? I'm sorry if I'm talking about to here. Number 3, okay. She was laughing up until that point. She was like, yeah, that's what. She's like, oh, okay. I don't think I've ever seen a Tahir with a backpack on, actually. Okay? To be perfectly honest. Number 3, what else do we have? Well, they tend to be smaller people because they are fast, so they have insignificant volume. And the big kicker is they have no attractions for people. You could have what? You could have People Magazine's Most Beautiful Person 2016 and 2015 to the left and to the right of them, and they wouldn't care because they're so focused on the teacher. Don't know what happened to the person. That's 2015, might have had a bad year. But the point is, how do you go from up to down? It's like you're not beautiful anymore. I don't know. Any case, the point being is that these represent the kinetic molecular theory. Now, if you can't remember these, what's a real student? A real student goes in curved paths because it is attractive. If it bangs into people into a hallway, it says, hey, what's up, Nick? What's up, girlfriend? Okay, they want to talk to each other. Okay, maybe creepy. They're like, get away, okay? Stop talking to me. Okay? They tend to be bigger volume because they go slower and they have high attractions. Okay, so how can I have low attractive forces? Well, I want the molecules of a gas to go fast. If they go fast, hey, they have less time, they have less ability to attract. So they must have the highest temperature. And you would want the lowest pressure on them so that they can be expanded. Right? Lower pressure on them, the gases will expand and have a bigger difference between the particles. So C is the best answer that gives you the most important part of this, the least amount of attractions. I went through that because who knows if they're going to go through the kinetic molecular theory. Okay, it could happen. So that was number 6. Number 7. My gosh, some of these questions you should not get wrong. We have a whole scenario of gases. They love gases under pressure. Okay, yes, yes, yes. Look at this entire scenario. My gosh, takes forever to read. What is this all about? Okay, the temperature is held constant. So the temperature is held constant in all of this. So the average kinetic energy stays the same. Average kinetic energy is proportionate to temperature. It's not the same thing, but the average kinetic energy is proportionate to temperature, okay? And we learned about that in our kinetic molecular theory equations, right? Okay, so that's that answer. It's that simple. Sorry, yes?
Is there a root mean squared on the
What's
test?
that? There is no root mean squared, but what they do want you to understand is that root mean squared, if you look at this, they want you to understand if I'm at the same temperature, let's make this CO2, and they're both, let's say, at 20 degrees Celsius. What they want you to realize is that if I have helium, this is the number of what? Molecules, and this is the speed. What they want you to realize is that the lighter gas is going to have a greater speed. Both of these have the same average motion. And I keep harping on this, even though I don't play a harp, okay? Because kinetic energy is equal to 1/2 mass speed squared. Now, we were solving for V to get root mean squared, but if I have two objects that have exactly the same average what? Kinetic energy, as my physics person now looking on, okay? If this value is the same and you got to keep it constant to each other, well, it makes sense that the higher mass compound, CO2, has to have a lower average speed, which would be root mean squared speed. And if you have a lower mass, like the helium, I'll do that in red to color coordinate, yeah, I'm doing this. Lower mass, you'd have a higher speed. So the average root mean squared speeds are what? Here and here are going to be different, even they have the same test. So the average kinetic energy is the same, but the speeds will be different. They love to ask that. So if they say, which one's going to escape an opening faster? The one that's going what? Faster, the one who has a very high average speed. Do not confuse speed with kinetic energy. Speed is a translational movement. It's from, let's say, A to B. Kinetic energy is translational movement, vibrational movement, and rotational movement combined. Smaller molecules translate left to right or right to left more. Bigger molecules will vibrate and rotate more. Okay? So the same temperature, same average kinetic energy, but the lighter molecule will have a greater speed. That's absolutely important. You will definitely see that every multiple choice I've gone over has harped on that. Again, I don't play the harp, neither does it. Okay? So number 8. Okay? They might tuba it. I'm not sure if that is catchy either, but okay. So, oh my gosh, look at this question here. They want us to know the what? The molar mass. They want to know what the mass of the unknown chemical is. This looks a lot like what? This looks a lot like question 1 of the same test in the free response. Absolutely the same kind of question. No, they weren't after what? A percent by mass? But you do it the same way. They want the identity of the metal chloride. So here's my unknown metal chloride. It's dry. Now, what do I have here? I added what? I added silver nitrate. Is that what they did? Yeah, they added silver nitrate. What does that tell me? Nitrates are always soluble, so I really added what? Silver ions and nitric ions. Now, what do we know? They told you the precipitate was AgCl. So when we dissolved M, we knew it was +1, and Cl negative in a beaker, and we dropped the silver nitrate, we know what? The silver hooked up with the chloride to make a what? A precipitate, and this hooked up. And then we did what? We dried it. We masked the filter paper first. We masked out the dry filter paper. We poured it over a filter. Then we dried it, and this is the grams of the silver chloride precipitate. So we added excess silver chloride. Sounds a lot like what we just did, doesn't it? This is in the same test. Look at the parallels in the same test. Okay, so what do I do here? Very simple. We do not have a calculator, so you should not be using calculators here. So look, they're helping you out. So the first thing I do is take my 223 and do what with it? I got to subtract out the filter paper, yes? Okay, which is 0.80. We can handle this. 3 minus 0, put that in your calculator, do not 3. Okay? This becomes 12 minus, carry the 1. I'm not sure if that's the same math now, okay, in Common Core, because I have no idea, okay? Okay, so we get 1.43, okay, and that's the grams of my silver chloride precipitate. Now look, party people, they made your life easy. What did they give you? Oh my gosh! They gave you the molecular mass to be 143. They're making your life simple. And I'm telling you, if you're not going through the multiple choice, you're not seeing the skills you need. What skills do we need? We have to be able to do what? We have to be able to white out our problems like this. No, we have to be able, okay, to do this. Do simple math by tens somehow. So what I have here is I have 1.43 grams of silver nitrate. And I want to get rid of grams and I want to go to moles, because I want to find out how many moles. That's what I'm trying to do here. It's precipitation analysis, just like the other question we went over in the part 2, for those that don't know what I'm talking about. In the free response question 1 we just went over, this is the one that is just like it. So my gosh, I wouldn't write this out on the test day because it takes too long. But if you don't know what you're doing here, be my host and do that. Don't be my guest, but don't be my, be my host and then take care of me. Okay, so get rid of grams. So what is 1.3 divided by 143? Okay, isn't that a tenth? Or is that 100th? What is that? Okay, and some people see that, isn't this based upon 2 decimal places, right? So this differs by 100. So this is 100th, right? 1.43, gotta get this down, guys. 1.43, you're gonna see this over 143. They're setting you up for easy math. I know you don't have a calculator, but this differs by what? 2 decimal places. So I know this is gonna be a small number by 2 zeros, so I know it's 0.01 moles. You with me? Now moles of what? Silver chloride. Now what's in the original compound? I'm looking for the what? I'm trying to relate the chlorine, yes? Why am I relating the chlorine? This is really, really important in precipitation analysis. Right? I've got my moles of my precipitate. Well, now we have to do stoichiometry. How many chlorines per one of these? So this is the moles of my chloride ion, yes? Correct. Now, if I get moles of chlorine, couldn't I just subtract that, okay? Or, okay, now I know the moles of chlorine. Couldn't I find the grams of chlorine? Yes. Okay, and what would be the molecular? So now I have the grams of chlorine, and I'm on my way to figuring out what's missing, okay, or moles. It doesn't really matter. So let me show you what I do from here. Okay, and there's so many different ways. People see this already, and I might not be showing you the way that you see it, but here's how I'll take care of this from now on. So now, let's get rid of some more stuff. So now that I have the moles of the chlorine, and they'll give you, this is a part 2, they give you a point for realizing it's a mole of chlorine. So this is equal to moles of chlorine, okay, ions. Okay, now what do I know about this? Okay, I'm trying to figure out what's the identity here. What's the molecular mass equal to? Grams per what? Moles. Okay, now, what do I know? Well, I'm trying to figure out the molecular mass, but I do have my moles of the entire compound, don't I? If I have 0.01 moles of chlorine, isn't there 1 mole of this per one of these? Yes. So what I really have is 0.01 mole of my unknown metal with the chloride. That's what I just did here. So that would go here. 0.01 moles. Okay. Trying to find my molecular mass. And then, of course, I need my grams. Okay. Well, if I know it's 0.01 moles, okay, I could find grams a couple different ways. Now, I know that I'm making this a lot more difficult for some people, okay? How else, what are your thoughts at this position? Don't take out a calculator, okay? You have the moles of your MCl, right? Okay, right here. That's what we just did here. And what do we know? Oh, we have the what? We have the grams. So 0.74, okay, grams per mole, over 0.01. Okay, now, what is that number? If I'm dividing by a smaller number, doesn't my number get bigger? It's another skill you must have. So it's equal to? So it's equal to 74 grams. Now, here's what I would do. Subtract out 35. Why? Right, and if I subtract out 35, I get approximately 39?
Yes.
Yeah, you get 39, which is the what? Mass of K. Seems like a lot of work. It's because I went slow. I'll go again. This is something you can do. I did what? Found my precipitate. Subtracted out the what? Filter paper. Subtracted the filter paper, I got the grams of my precipitate. Converted to moles, it was an easy number. Got 0.01. Realized that there's a ratio between 1 chlorine per 1 silver chloride to 1 chlorine in the compound. So therefore, it's the moles of MCl. I know molecular mass is what? Equal to grams per mole. I had the mole, I had the grams. I get the molecular mass of 74, subtract out the 1 chlorine, and I get 39. I know chlorine is about 35.4, so subtract 35 from that, and you get about 39. And who has the atomic mass of 39? Potassium, and that's why I knew it was KCl. All right, so this is on the same test. All right, moving forward. Questions? Did I confuse anybody? All right. All right, moving forward. That was 8, so let's go to 9. Is this 9?
No, you think you're right.
Yeah, I'm good at whiting stuff out. It'll be all white. Yeah, I know. 3-hour review session, it's... Okay, I don't know what just happened. I think it just went down to the last page. Okay. Number 9. Okay. Taking forever to go through these, but I hope you're picking up the concepts here. Okay, during the course of the experiment, my computer is lagging. Okay, number 9. Number 9. During the course of the experiment, which of the following happens to the nitrate ions? What would the nitrate ions do? Nothing, because nitrate ions are what? Spectators, because they have what? Why are they spectating? In terms of Coulombic attractions. Right, they have a small charge density, which means they have a lot of atoms with a little bit of charge. Their Q is really small, the charge, and their distance, their radius is pretty high. Okay? That would give me a small charge density or small, so they remain dissolved in the filtrate. My gosh. You want to give me that question? I'll take it. Okay, moving forward. Maybe. Okay, number 10.
I love these.
Yeah, we should love and we should cradle these. Okay, so maybe if I can get there. Christmas. Okay, so when. Okay, now how do I do this question?
Skip the question.
Did I?
Yeah, we're on 10.
Okay, it happens to me. Thank gosh you're here. Oh yeah, that's something we did. So we like these questions. Okay. Darn it, I thought someone liked the acid-base questions. All right, another lifetime. All right, so which of the following best describes silver nitrate solution before the reaction? Right, so occurs before the reaction occurs. Now what's the reaction? Okay, oops, let me just go there. Before the reaction was that we have MCl, okay, dissolved, and then we're going to add the silver chloride. Okay, so before the reaction, so what do we got here? Okay, well, we have, look at A, silver nitrate, and this is the negative part of water, the oxygen surrounding it. This looks all good to me. I'm not sure what they mean by before, but this is the silver nitrate. That doesn't make any sense because the orientation is switched. The positive end of the water would be, so I can get rid of that one, right? These are the famous boyfriend, famous girlfriends. The water would not be oriented both ways. It'd be definitely the what? The positive hydrogen end would not be attracted to the positive ion. So for many reasons, I'm getting rid of B. I feel like I'm on The Voice or something. Okay. Okay, so this is, oh my gosh, it's all about molecule ion attraction. So gosh, this is the negative ion attracting the positive. I like that. This is the negative part of water attracting the negative. Makes no sense. And of course, if I do D, duh, this is showing them together as a solid. And for reasons we know, nitrate is always spectating. So I will pick A for my team. Okay? Or A is the correct answer. Yes?
Can I go get a drink from the water?
Yeah, you can get a drink. You're going to slurp it or you're going to cup it in your hand and bring it back?
I feel like Nick's a slurping kind of
Yes.
guy.
I think he's going to slurp me too. Okay. Number 11, which is what people did not like.
I'm sitting here. My legs got started cramping.
Okay, intermission's over. Number 11, they're adding what? Strong base to strong acid. We would get a pH of 7 if we have exactly the same amount of acid as base. But how many times have I asked you to figure out the moles of acid and moles of base? 1,000,000 times. So for the base, okay,
No.
I'm going to take 0.20 liters. Where did I get that from? Right, I'm going to times it by 2 molars, that's moles per liter. 2 times 0.2, I can do this. We don't need to calculate it. Is 0.4,
What?
and that's moles of base. Oh, changing the color because I can. Here's my acid.
America.
Yes. 0.5 liters because it's 500. I'm going to times it by 1 mole, molarity, which is moles per liter. You might, okay, and you get 0.5 moles of the acid. So clearly, we're not going to be in a what? We're not going to be in a neutral pH because we don't have the same, and we're not going to be in a basic range. That I should not have to explain. The question is, will it be 1 or 3? Okay, well for me, party people, what's left over? The base gets totally annihilated because there's enough acid to do so. So I have 0.1 moles of acid being added to what? 700 milliliters. So if I got 0.1 mole acid, let's pretend I'm a princess and this becomes a liter. Now I know I'm what? Estimating 300 more. But when I do so, I'm getting 1 times 10 to the negative 1. What's the pH of that? pH of 1. Now it's not perfect because I had to, it's probably a little higher, but I think it's because of that it's pretty darn close, and just by estimating, A is a better answer. For B to be the answer, you would need something that was what? 100 times less acidic. 1 times 10 to the negative 2. So you may think, Mr. Grodsky, that little 300 milliliters makes a big difference, but think about it. To be a pH of 3, that would have to be 100 times more acidic. It wouldn't make it that much more. So A is the best estimation. They love estimations.
No, okay.
Okay. Not sure what that was, but hey, I'm tall. Number 12. Alrighty. My gosh, this looks familiar. Number 12 says, the table above shows the first ionization energy of the atomic radius of several elements. Which of the following best helps to explain the deviation of the first ionization of oxygen from the trend? So here's the oxygen. First ionization energy for the millionth in one time is the energy that takes the pull electron away. So my friends in chemistry, look at this. Boron, don't be one. Carbon is increasing. Nitrogen. By the way, if we look at a periodic table, we're going across the periodic table. Okay, we're going across row 2. Okay? N equals 2 here. It doesn't mean anything. Buckanopi. Now, so if you look, oxygen, so all of these go up, but oxygen goes down. So if I was plotting these guys, we would see them go up, 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 and then what? Down, and then back up, and then back up. Okay? So why does the oxygen drop? Well, if you look at and understand something called Hud's rule, okay, and know that when we deal with oxygen, it's 1s2, 2s2, 2p4. Now, if you don't know that, you go to your reference table, and you can see, maybe, if I was to make this smaller, okay, and we can see 1s2, 2s2, 2p4. Wasn't that special? Yes, it was. Okay. Now, what do we know about the p's? Well, there are 3 orbitals. If I do orbital notation, there are 3 orbitals. No, they're not shaped as boxes, but I draw boxes to show how the electrons pair up in the same orbital. Those are supposed to be the same size, but again, I have issues. So there's my first, second, third, and now we have to start pairing up. So because oxygen is the first place where we have to pair up electrons, it's the electron-electron repulsions that make this electron feel the nucleus less. Think about it. If I'm repelling from electrons, electrons are pushing back on me. Here's my nucleus. That's attractive force. Here's an electron. So I should be what? Be pulled in by the protons. But if there's another electron in red that is pushing me away, right? I feel that nucleus less, therefore I need less energy, I need less energy to be removed, okay? So this can be removed easier because of that. So we've spent a lot of time on that, probably too much, but there's a question. So we would say the repulsion between paired electrons. And by the way, there's no paired electrons in the nitrogen. In nitrogen, you have 2p3. So you would have a scenario where they're not being paired up. If you didn't understand Hud's rule, you might write them this way, not with these ugly boxes. You might just do this, and that is bad chemistry. Yes. Okay, so number 14. Or 13, yes. Thank God there's someone there for me today. Okay, I'd be skipping, like, we're going through this pretty fast. All right. All right. It's your problem. It's plenty of time on this test for this. Okay, now, moving forward. I know. It's cool in here. I know. There's nothing like doing this on the Wednesday of our break.
Mr. Grotsky, I've been up for so long. Like a whole 2 hours. It's such a demanding break.
I mean, no one can.
Yeah, I know. I'm just pointing it out.
Especially me. Okay.
Maddie, do you care? Wow.
Okay. So Riley's been my video forever. Number 13.
I didn't know we were recording.
That's why you're being like.
Riley, this whole thing is being recorded.
Cut
Which
it
of the
out.
following equation represents a reaction for which the standard entropy change is positive? My gosh, how many times have they asked for this in part 2? Entropy, very simple, is delta S. And delta S is the measure of what? Dispersion of energy and or, what parallels dispersion of energy is disorder. Okay? So it's positive when energy is being dispersed from a concentrated source to a less concentration, or we increase in our disorder. So we want it greater than 1. Well, we have 3 gas molecules becoming 2. That would give me a delta S that's negative. And they could ask for that, and they have in part 2. And why they could ask for you in part 2 and say, why is that a decrease in entropy? And the best way you explain that in part 2 or in the free response section is saying, we have 3 molecules of reactants, and now we just made 2 molecules of products. We've lowered the overall number of what? Molecules. You go from 3 to 2, you're becoming more ordered. You're putting them together in A. Look at B. You're putting them what? Together. You have 4 I'm sorry, I can't count, 3 molecules going into 2. We're stuffing these guys and putting the energy back into these. Here is our answer. We have a solid that's breaking apart into 2 particles, and one of them is a gas, which is what? Making the energy much more dispersed as it leaves. Okay? But anytime they ask you about entropy in an equation, count the number of reactant molecules to product molecules. If the product molecules are increasing, you're increasing the disorder. Also look at the phases. If you're making a liquid to a gas, okay, clearly the disorder is increasing because you're dispersing that energy. D is for the same reason you're putting stuff together. Should be an easy question, but the concept here is in part 2. Okay, now I think I'm at 14. Okay, imagine this. A container filled with gases. They are in love with gases and they're in love with acid and base. So am I. So it's a triangle of sorts. Okay. Now, or it's an octahedral. Sorry. Okay.
Oh my god. That's too many.
Yeah. I'm sure there's 6 other
Love
people
square.
involved. Yeah. It's a love square pyramidal. Okay, I have problems. I get it. All right, 14. On the basis of the data provided, the gas in container B could be what? All right, so this is thinking on your feet. What do I notice? I notice that the pressure is about the same for all of the gases in the container. Now, what do I know? This is a Dalton's law of partial pressure. What do I know? Well, I know, party people, that if I'm in a container, that all these gases are what? Proportionate to how many of them there are. So if I have this, they're all under the same pressure, okay, pretty much have the same partial pressure. If they asked you for the total pressure in the container, we should know by Dalton's law, the individual partial pressures equal the what? Total. Good, we've been down that road. But in this question, they're not giving you the mass of the helium that's in the center, but they give you for SO2. And that's the key to the problem. They want to know what 3 is. That's 16 grams. I've got to relate this to what? How do I go from grams to how many collisions occur? Moles. How many particles are creating that partial pressure? So I'm going to take this and convert to moles. And if you go to the periodic table, sulfur is 32. Oxygen is 16 plus 16 is 32. 32 plus 32 is 64. 1 mole of SO2 basically got me what? The 2 atmospheres of pressure. And since the pressures are very similar, then it must mean that a mole of this compound is 16 grams. That's the concept. If I've got the same partial pressure under the same conditions of what? Temperature in the container, then if I have a certain number of moles, this has to be the same number of moles. Particles in a container create collisions. These are creating the same collisions, must be the same number of molecules. Now the mass is different because different atoms have different masses. So this is a mole. So all you got to figure out is which choice adds up to 16. That's all that was. Look at choice A. Carbon is 12, plus 1, plus 1, plus 1, plus 1 is 16, choice 3. The key to the problem was seeing the pressures were the same, the number of particles had to be the same. So giving you the mass, this told you it was at 1 mole, and you go to your choice and see that methane is 1 mole. Okay? That's all that was. A relationship. And I get it, you may miss that because you're overthinking it and you may get some wrong. But that's all that question is. There's an easy answer. Okay, next question. Under conditions given, considering gases, containers 1, 2, and 4, the average speed of the gas particles is what? Okay, we've been down this road before. Okay? So who's going to go fastest? Choice 1, the first container. Why? It's the smallest mass. And they love to ask this question. Why? Kinetic energy, which is equal to 1/2 m speed squared. Yes?
I have a question on number 14.
You bet.
Would it not be oxygen because it's 2 of them?
Right.
So the mass of
Oxygen
oxygen.
gas exists as O2. all the Hofbrinkels. It's a great question, because you may say, well, it's oxygen atoms. But remember these guys, the Brinkel Hofs or the Hofbrinkels, whatever your teacher taught you, I don't care, I used Hofbrinkels. Okay, these guys are all what? In their elemental form, they exist as diatomic element. So the Hofbrinkels. So yes, great question. It's not oxygen because oxygen exists diatomically. Great question. All right, so everyone understand 15? The lighter the one, and again I keep writing this because they could ask you why. Lower the mass, higher the speed for the same temperature. Do they all have the same average kinetic energy? Yes, because they're all at the what? Same temperature, correct, but they have different speeds. Excellent. You will see that Monday, somewhere in your test. It's on every single released exam that I've seen here. Okay, 16. The best explanation for the lower pressure in container 4. Now, look at this. Why would container 4 have a lower than expected pressure? They're keying on something that the other tests have not, that could pop up. You need to understand something. If I'm like Tahira, unlike Tahira, and we are real students,
Oh my god.
when I go to the what? When I go to the printer, here's the printer, okay? Here's the table. The table's in the classroom. Tahira is sitting here. We're looking down. She does not want to miss anything I say, so can you get the worksheets in the printer? Tahira knocks into Nick, climbs over, gets it, and flies back. Fast. She has no attractions to the people around her. Now, if I ask Nick, let's do someone else. Let's ask Lily. So Lily's sitting here. She's not going to go a direct line. What Lily's going to do is she's going to say, "What's up, peoples? Hey, yeah, what's up? What's up? What's up? High five. Yeah, let's go back over here." Eventually back to the printer because Lily is attracted. Okay?
It's called Lily Unideal.
Are you saying I don't like people and I just don't understand?
You're an ideal. No, I'm giving you a compliment. You're an ideal student, an ideal gas. Okay? Lily's the problem. Okay? She's the what? Real gas that really has attractions. How do gases deviate from ideal behavior? Their pressures are lowered. Why are their pressures lowered? And they could ask this, people. Gases that are ideal go in straight lines, correct? Gases that are non-ideal or real, like Lily, tend to go in curved paths. Now, if they go in curved paths, I can't speak, okay, they hit the container wall, or it takes them a longer time to hit the container wall. So their pressure is what? Lowered. So these are supposed to be all 2, but why is SO2 lowered? Because it's acting as a real gas. It's the biggest. It's the slowest. It's the one with the greatest attractions. SO2 is a SO2 actually is a polar molecule. So the best explanation would be they have a larger average speed. No, they would have a slower speed because they're what? One of the heaviest. So that makes no sense. They occupy a larger portion of container volume. They do, but still insignificant because they're still so tiny small. They have stronger intermolecular attractions. Okay, that's the key here. Because they have attractions, they're deviating from ideal behavior. That's what that question is about. And they will pop up. Maybe as a picture question. I can see this as a picture question. Pick the real gas. And you're going to pick the gas that what? Curves. And I believe you're going to see something like that. I really believe. I haven't seen in these 3 tests. It's very possible. Okay? That's what this question was hitting. That's why it's good to review these with me. Okay, everyone hates this question. You're going to see this graph. Maybe not written like this, but you will see this graph. Okay? Bye-bye. Rock on. Easy listening on. Couple on. Okay. All right. There are cameras in the building. Okay, now what we have here is internuclear distance with potential energy. Okay? Now, what's happening? Here are atoms that are unbonded, A and B. And they have a certain potential energy, which is usually pretty high compared to their bonded states. Why? Because A and B, my friends in chemistry, haven't used each other to secure a what? Configuration that's stable. The reason why atoms bond is to get stable, right? In the case of, let's say, hydrogen, hydrogen has one valence electron, another hydrogen has another, and they use each other to both achieve a configuration of a noble gas. This is, they both feel like they're 1s2, which equals what helium is. Okay, not helium negative. All right, so right now they have higher energy. When they start coming closer together, what happens is their nuclei, which is positive, start attracting each other's electrons and start to feel some stability. The stability what? Reaches its maximum, or we would say negative potential energy. Why does the energy drop? Because they're getting more what? Stable as they get closer together. So we would say the stability is increasing. I'm going over this because you're going to see this graph. This is a graph that pops up. So this represents the greatest stability because it's the greatest loss of energy. Energy is being lost, okay, here, given off. And what do we know? You should know this. When atoms form a bond, always form a bond, energy is released. They form a bond, they create a stable scenario. Okay, their electron configurations are more stable in a bond than they are. So therefore, energy is lost. So this represents the maximum position. This is the strongest bond here. Now, we do know that if we keep getting closer, you should realize this. As you go this way, you're getting closer. Now, what's happening? We've reached that point of what? Positives, are these negatives attracting each other? Are these positives attracting the negatives? Is balanced off by the what? Repulsive forces that these what? Protons in each of these nuclei feel for each other. So if you keep pushing them closer, you start to have repulsive forces. And that's why the energy starts flying up. And that's why you learned last year nuclear fusion takes a tremendous amount of energy when you try to slam nuclei together. Look what happens to the energy level. It goes up. All right, so as you put them too close, they repel. So in truth, there's a balance here. There's a balance of attracting the electrons and the balance of the repulsive forces. When they are balanced off, we've got the strongest bond. Now, as we've learned, you should know, they vibrate in their bond positions. They go up and down. And that's how infrared, how the molecules can absorb energy by how far they rotate up and down. Any case, back to the question. Okay? Okay, We have three molecules, X2, Y2, and Z2. Okay, which one is H2, N2, and O2? That's the question. They want to know which one of these. So let's clean this up, because I got stuff all over the place. Kind of like my room. Okay, but I like it. I can grab stuff when I need it. Okay. Now, which one is H2? Who's the smallest? Who's the smallest of the three? When N equals 1, doesn't that index size? So who is going to be close enough together before they start repelling themselves? Who has the least number of protons so that they actually get the closest before they start repelling? Can anyone see that X2 is going to be H2? Because it only has one proton, and I'm using that based on the choices. I have H2, N2, or O2. N2 is the smallest, and it has the least number of protons. So these guys can get actually closer. Remember, going this way, you get closer before they start what? Repelling up. So this is H2. So now I have O2 and N2. Now they're pretty similar with proton strength. So I can't really decipher them based on who comes first and second, possibly. But wait a minute. What's the big elephant in the room? The dip, right? Dip, or I don't know, can you say that? Now, the biggest dip in the room is right here, or me, or Spencer. I meant to say that. Okay, now, hey, Spencer's here. All right, now, this guy got the what? Most stable. He has the greatest strength of bonds. So that's right, the second bond. Now if I compare the bonds between the we see that the nitrogen is the triple bond here. That's right. Okay, now nitrogen has triple bonds. What does oxygen have? Double bond. So who's going to be more stable? Nitrogen. So that's why the biggest dip isn't Spencer. The biggest dip is the N2. And the oxygen, okay, you notice it's a little dip farther? Okay. So when we do the problem, we have who? We have X2 is H2. There's a Y in the middle, yeah. And H2, N2, and O2. That's why it's choice A. Or we say if we're phonetically doing this. Okay. Any questions there? I spent time only because I know I've spent time in other because that's when you're going to see. You can see in a part 2. Am I going up or down? 17, 18. Do we need a break? Want a little break?
Me too.
More down.
All right, back on the horse. Back on the pony that's spontaneously taking me somewhere, as opposed to carrying the pony up the hill. No more of those metaphors. Coming soon. Okay? Okay. We're almost done with this course, but not yet. So number 18. Gosh, I've seen this one over and over and over. It seems to be they love about simple calorimetry. So in my opinion, okay, it's really good to draw. Now you probably don't need it for this question because they want you to understand what specific heat is. If you've been through enough of these tests, you realize they're always talking about specific heat, okay? But in any case, I got a 10-gram cube of copper, okay, is placed in an insulated cup containing 10 grams of water. Okay, that's not a lot of water, but we have an insulated cup. Okay, we've got the cube. Okay, if it is a cube, yep. It's 10 grams of the copper cube. It's in some water. And T1, okay, I guess, temperature 1. So we have the copper at T1, okay, is placed in a insulated cup of 10 grams of water at T2. So the water's at T2. Okay. If T1 is greater than T2, so that means that the block is what? Warmer. Okay, so let's just make it another one here. Let's make it, let's say, 80 degrees Celsius. And the water is at they said T1 is greater than T2, so that means the block is hotter than the water, 40 degrees Celsius. Which of the following is true when it reaches thermal equilibrium? At some point, the temperatures will be the same, obviously. Okay, heat flows from hot to cold, and it'll keep doing so until they reach the same temperature. What they want you to understand, they will not lose the same amount of temperature, or I should say, they will lose the same amount of energy, but the temperature change will be different because of this. Q, the energy that's either released by the copper or absorbed by the water is equal to the mass of it times the specific heat of it times the temperature change. Now, what do we know? Well, they tell me the specific heat of copper is lower than the specific heat of water. Let's make copper red, okay? So we have the Q of the copper that's released is equal to the what? Q of the water that's absorbed, mass C change in T. We know that these values are equivalent to each other. They have to be. Now, of course, there is some heat loss. Okay, it's not a perfect system or isolated system, but hey, neither am I. Okay, but what do we know? The water, the blue, because water is blue, right? All right, at least in my drawing. Water has a higher specific heat. Copper has a lower specific heat. What does that mean, party people? If these Q's have to be the same value, the temperature change has to be lower for the water. And the temperature change has to be higher for the copper. They continually want you to understand this. This might be the third time I've seen this type of question in a multiple choice. Now, what is specific heat? For those that are still not sure what this is about. If you solve for C, you get the thermal energy over the mass times the temperature change. And this means, all right, this is the energy that it takes, Q, is the energy it takes per 1 gram per degree Celsius. So it's the energy required to raise a gram of a substance 1 degree Celsius. Or Kelvin, doesn't matter. Why? What's so big about that? Well, If I've got a smaller specific heat like copper, I don't need much heat to make a big temperature change. That's why the what? The copper is going to have a bigger temperature change. If I have a bigger specific heat, like water, water resists temperature changes. I need a lot more what? Heat per gram per degree Celsius, because water resists temperature changes. By the way, why? Why does water resist temperature changes? Water, if it has thermal energy, is moving, right? Oops. Gosh, I've done that a few times in these videos. Why does water resist temperature changes? What is keeping it from moving? The H bondings are significantly stronger. They prevent a lot of motion, okay? Whereas in copper, you've got what? A sea of mobile electrons that are just free for having a party. Whippy! Go anywhere I want, so they can certainly move around. So in any case, what's the answer? The temperature of the copper changed more than the temperature of the water? Yes. Okay, the temperature of the water? No. Temperature of water and copper changed the same amount? The heat, understand this, temperature is not heat. They're proportionate to each other, but not the same. The relative temperature change of copper cannot be determined, no. So the best answer is A, or A, okay? Now I know you spent a lot of time on that, but this is one, circle it. It's one we see over and over and over. You bet your bottom dollar, bet your donkey, don't want to say, well, I'll just keep it that way. Yep. Bet your donkey you will see a question like that. It's over and over again. Here we go. I've been waiting for an acid-base question. Yes. Okay, another acid-base question. A solution containing hydrochloric acid and, ooh, that's an acid because I see an H in front. Is that a strong acid? No, it's a weak acid, okay? Has a pH of 2.4. If enough base is added to a solution to increase the pH to 10.5, the amount of which of the species increases as KOH is added. Again, draw if you have to. First of all, I have HCl. What does that really mean in my wavy water? I have free what? H plus and Cl negative. They're never together. It's a certain wedding I keep mentioning. Okay? Never together. Okay? Now, now HClO2 is a weak acid. So my friends, in chemistry, we write it together. Okay, now we're going to add some drops of Jupiter. And in my drops of Jupiter, I have hydroxide ions. Na plus, but we know better, it just what? Actually, this is KOH, so it's K plus. So I'm going to add hydroxide ions. What's that going to do? Is it going to yank the H away from Cl? No, so we know right away the Cl is not going to increase, right? In fact, the Cl negative ion stays constant, doesn't it? As much HCl I added, that's it, there's no more. Does the H plus steadily increase? Not if I'm adding a base, okay? Now what's happening? Doesn't the strong base forces the weak acid to give up its proton? Yes, and what it produces as a result is the conjugate base of the weak acid. So as I keep adding the strong base, it keeps forcing this to become this. So the conjugate base keeps increasing. Now some people would say, well, wouldn't this react with water to reform this? Well, yeah, some way, but there's still going to be a lot more of this because it's got something called a KB, which means it doesn't completely dissociate. It's a weak base. So it's not going to all go backwards. There's going to be a heck of a lot more of this. Okay? So the answer is this. And this is just a question. Do you realize that weak acids make conjugate bases? And this is an offshoot question because somewhere, somehow, Monday, they want you to realize that a weak acid is going to make the pH at equivalence equal to what? At 7, above 7, or below 7? If I drop a strong base on a weak acid, at the equivalence point, is it going to be above 7, at 7, or below 7? Above 7. And the reason is why? The conjugate base you just made in water is going to do what? It's going to yank an H away to reform the acid a little bit and produce what? Hydroxide ions. Now they could do this, I believe that you are either going to see this or the opposite. What if I drop a strong acid on a weak base? What would be the resulting pH? Below 7, because in that case, the weak base will make the conjugate acid who will protonate the water to H3O+. Be aware of that, because that is an important concept. I haven't seen in these 3 tests the weak base to strong acid combination, so I really think you're due for that, okay? Although they keep pounding weak acid, strong base, all right? Again, hopefully you're seeing these things. Over and over again, these are the same concepts. Okay, classic Grotsky, writing over. Okay, at some point I can erase. Okay, this thing is lagging, so am I. But not sagging. Okay, not yet anyway. Come back in 10 years. I might just be a pile of mush teaching. Okay. Back when I was younger, at 50. All right, now, halfway to 100, not yet. Here we go. Now, 20. So this is another question that I see happening a lot, party people. They want to mess with your understanding of pH. What is pH based upon? pH is based upon the idea that we have water, okay, and I'm just going to white out the top to make some room here. I don't know why I have to narrate that. Okay, so if I have some, let's see here, we'll go blue. So I have water doing this by itself. H2O breaking apart, it's called autoionization to H plus and a hydroxide. We know this is an equilibrium. And we know that the equilibrium constant is equal to what? Well, products over reactants, coefficients become exponents, solids and liquids do not apply. We just get this combination. We don't have any reactants because this is a liquid and these are aqueous. This equals K, but more importantly, KW. Now, KW is equal to 10 to the negative 14, correct? But that's at a certain temperature. Equilibrium constants are temperature sensitive. So once you start changing the temperature, you start changing KW. Now, when KW is equal to 1 times 10 negative 4, and by the way, I believe that's 4 degrees Celsius, okay? This has to equal what? The same number times itself. This becomes 1 times 10 to the negative 7, and this becomes 1 times 10 to the negative 7. And we know pH for the millionth and one time is equal to the negative log of that concentration. And that'd be 7. But when the temperature increases, we're watching the pKW, which is really the KW negative log, okay? Overall, it's going down. It's going down. So my KW is decreasing. Now, if my KW decreases, let's pretend I'm a princess again, and let's decrease KW. Okay? Now, when I decrease KW, at some point, let's wait for this, here we go. Let's make it 10. Now, it's getting smaller, right? So make this 10 to the negative 16. My pKW is getting smaller. You see that? Okay? Now, think with me for a second. If my pKW is getting smaller, all right, that's the what? Negative log. So this is becoming what? Smaller. Now, if I make this number smaller, okay, what do I have? Well, I'm making this number up. Wouldn't this be 1 times 10 to the negative what? 8. Okay? And of course the pH would be what? 8. Now, you notice my number here is not consistent. What would be the pKa of this? What would be the negative log of this? 16, right, if it's a pKa. So I'm not going in the right direction, all right, or am I? No. Okay, so let's do it the other way. Now again, I'm just, again, showing you what this means. Let's make if the pKa is going down, that must mean that my KW is getting bigger, correct? Okay, so let's write it. Let's make our KW 10 to the negative what? 12. What must this be? 1 times 10 to the negative 6, and the hydroxide 1 times 10 to the negative 6. Are you with me? What would be the pH at neutral pH if in fact the KW increases? The neutral pH would be what? 6. When these are equal, the pH is 6. See, we fall in love with the idea that neutral pH is always 7. 7 always means these are equal, but that's only when we're dealing with a KW at a certain temperature. When you change the temperature, this value changes, which changes this. So just playing with the numbers, knowing this KW, PK, what's the negative log of this? 12, which is lower than what? 14, correct? So when this PKW drops, that means that this number is getting bigger by a negative exponent. And these numbers have to be the same. So the new neutral pH is now 6. The whole standard changes. We don't often talk about that. It doesn't mean that all of a sudden the water got acidic, does it? Because these guys are still what? Equal. We've seen this question before. So now the question is, why? Why? Have we seen this question kind of before? I change the temperature and the equilibrium constant's changing. If my KW is getting bigger when the temperature is increasing, where is the K moving? Toward the products or the reactants? Who is it favoring more? How many times do I draw this? I draw this for good reason. What am I going to draw now? You've been with me so long now. What am I going to draw? If I'm going to draw equilibrium.
The horseshoe.
Yes, a horseshoe, right. What's in the bottom? K. This is KW. Where is it moving if KW is getting bigger? Because I know the pKa is dropping, which really means the KW is getting what? Bigger, right? This negative exponent went from 10 to negative 14 to negative 12. This is a pKa of what? Of 14. This is a pKa of 12. So when the pKa drops, it just means that this number is getting bigger. So when K gets bigger, what is K equal to? Products over what? So there's more products. So that means that this is moving what? This way. Correct? Now why would K move that way? Well, think with me. Stress response. If I increase the temperature, look at this. I increase the temperature. What is the reaction? What's the response to what? Decrease the temperature by favoring the what? Favoring the endothermic reaction, correct? Wouldn't the endothermic reaction eat up the temperature if the energy is on the what? Product side, correct? So all of this question was about was seeing that. We've seen that before. Look at the reaction again. Stay with me. I know I'm making a lot of explanations here, but because you're going to see this again, mark my word. Here's the energy. Has to be on the what? Reactant side. Plus water breaks apart into H plus and OH minus. Has to be. Because if the KW is going and favoring the products, okay, with an increase in temperature, I'm seeing an increase in temperature, it's because the response by the reaction is to lower the temperature, which means use up the endothermic way. So when you increase the temperature, you always favor the endothermic way. It's more spontaneous in the forward. Okay? So, back to the problem. Based on the information above and all my explanations, which are the following? The association of water is exothermic. What did we just find out? Right. If the K is increasing and temperature is increasing, by the way that I just explained it, we know it's always endothermic in the forward. The pH of pure water is 7 at any temperature. Wrong. That number changes. In the case that I showed you, pH could be 6 and still be neutral. As temperature increases, the pH of pure water increases. Okay, let's think about this. When the temperature increases, what actually happened? Okay, the pKa got smaller, which means this number gets bigger. So 10 to the negative 12, if we just use that number, each of these is 1 times 10 to the what? Negative 6, so the pH dropped, correct? So as temperature increases, the pH of pure water decreases, choice D. Tough little question there. But look what it did. It made you think about equilibrium. I can see getting this one wrong. But I'm seeing pKa and pH happen all over. Questions? Did I make you understand that? Okay, I know I spent a lot of time on that. But you can see where equilibrium is. I've seen this question pop up. So did I get that right? As temperature increases, the pH would have to be smaller at a neutral pH. Yes. Okay. Is KW. Good. All right. Moving forward somehow. As this thing is. La la la. Okay, it's not like I'm here. Okay. Yeah. Okay. All right. Here we go. CO plus 2H2 gives me this. Delta H is less than 0. What does that mean? What's it screaming to you? It's exothermic, which means the heat is where? On the product side. That's what they're screaming. We may need it or not. But I'm going to write the heat right there. All right. The synthesis of CH3OH from CO2 and is represented by, look what they gave you. They gave you the Kc. My friends in chemistry, what's the common theme in these questions? Besides acid and base? Equilibrium, equilibrium, equilibrium. Have we seen in almost every problem? The last problem is equilibrium. Okay? All right, 21. Or as we say in Deutschland, und 20. Okay, now, 21. Which of the following explains the effect of the equilibrium constant Kc? Mr. Grotsky, what's Kc? What's Ka? What's Kb? What's Keq? What's Ksp? It's all the same freaking thing. Kc just means equilibrium constant. We're using concentrations. If you see Kp, what do you think it's talking about?
Pressure.
Pressures. And if you were to write, I haven't seen it in a while, so it could pop up. If they ask you to write an equilibrium expression for gases, do not write brackets. Write parentheses for partial pressures, okay? They may take off for that. I haven't seen it in the release tests. I feel like you're due for that. I know it's totally off the reservation here in terms of the question. All right, 21. Which of the following explains the effect of equilibrium constant when the temperature is increased to 650? Does this remotely seem familiar to the last question? We're at 483, yes? And now the what? Temperature is now what? Increased. We're changing the temperature. What is the K going to do? This is the same principle as the last question. If you don't see the parallels here, okay, then I'm doing a terrible job. And I hate doing a terrible job. So I'm locking the door and we're here for 4 more hours. No, just kidding. Okay, now. I'm breaking all kinds of laws right now. All right? So if I'm doing a terrible job, I'm going to get fired, by the way. Okay. Now, if the temperature is increasing, okay, how does the K change? I'm going to draw it. I'm going to figure this out. Let's think about this. Well, the temperature is increasing. I know it's going to make a change, so I'm going to use my little stress response. What's the stress? The temperature is increasing. What would be the response by the reaction? To decrease the temperature, always do the opposite. Now, how do we decrease temperature if we increase it? We're going to favor the endothermic way. It's going to be more spontaneous in the reverse. It's going to be another Beyonce to the left. Okay? So I'm going to go that way. Everyone see that. Anytime you increase the temperature of a reaction, anytime, they could ask this in part 2, the reaction is going to shift, okay, to favor the endothermic to lower the temperature. The endothermic uses up the heat to go this way. So that would mean in this case, K is going to move to the what? To the left. It's going to get smaller. It's going to favor more reactants. So the Kc, Keq, Ksp, it doesn't matter, will decrease. And there's only one choice where it decreases, because the reaction is exothermic. You're going to see that, see that, see that, and see that again. In this test, we saw it back to back. Back to back. They're stressing that. They're screaming to you. You better know this because you're going to see it. That's why I think it's so important. 22. 1 mole sample of CO2 and 1 mole sample, 1 mole sample of CO2 and a 1 mole sample of H2 are pumped, so am I, into a rigid, previously evacuated 2-liter vessel, okay, at 483. Oh, you pumped? Okay. Which of the following is true at equilibrium? Okay. My friends in chemistry, they're starting you with what? They're starting you with a mole of each. Okay? So a mole of each, one of these. I've seen this question over and over. Okay? Now, my friends, this is before the reaction has reached equilibrium. Okay, so you could clearly see that Q is going to be what? Okay? There's 0 products. There's so many more what? Reactants than products, correct? So Q is going to be so much lower. Okay, so Q is in this region, so the reaction is going to go what? Q is lower. So the reaction is going to go forward. Now, how much forward does it go? Yes?
Why wouldn't it be 2 moles of H2?
I don't know. Did they say 1 mole of each or no? Yeah, they said 1 mole of each.
Okay.
Okay, that's why. All right, thanks. I could be wrong sometimes. I often I am. Okay, now, so my friends in chemistry, they had a mole of each. Clearly, this is not equilibrium yet. So Q is going to be tremendously high. This reaction is going to go forward to get to K. Now look what the K value is. 14.5, yes? So who's favored? At K, isn't the products favored a little bit? Yes? So this reaction is going to move greatly in the forward, and it's going to favor more what? More products, generally speaking. So look at my choices I'm going to get rid of. Which one is glaring that I'm going to get rid of? Can all of these be equal? If the reaction is favored so much with the Q originally, okay, this reaction is going to come down. Okay, now, is K equal to 1? If it is, then this is a possibility, but it won't still because of the math. So I'm going to get rid of D, because they're never going to be equal. Okay, that's one you get rid of. Now, look at choice A. A is a stoichiometric relationship. H2 is equal to 2 times CO. Now let's look at that. H2 is equal to 2 times CO. Let's think about this for a second. Now, it's not the answer, but I want you to see what we're dealing with here. What's the stoichiometric relationship here? There is 2 H2s per every CO. So what does that mean? That means this, that we're going to lose, remember we did this equilibrium stuff, minus 2x. This is minus x, right? So what does that mean? We're going to lose twice as much H2 as CO. Now, does that mean that the loss of CO is going to be twice that of H2? Look at that relationship there for A. Is H2 equal to 2 times CO? No, it's actually equal to what? A half, right? So that doesn't even make any sense, so I get rid of that. Now, is there any possibility that that could be right if it was written opposite? If I said that the 2H2 equals, or I said a half of CO, the half of H2 equals CO, that still wouldn't be right, because a lot of this stuff is going where? To the product side. Because products are favored, there's no way that that relationship based on the coefficient will ever be correct, unless what? The reaction completely goes to completion. Because it reaches equilibrium, that 2-to-1 ratio will not be correct. Besides, we added what? A mole of each, which means what? Half a mole of something's going to disappear. If I had a mole of each, do it quickly in your head. If I had a mole of each, this is a mole, this is a mole. Isn't this going to be half? All right? So I would lose 0.5 of this mole. I'm sorry, so this is a mole and this is a mole, correct? Now this is twice x. So I would lose what? All of the mole, and who'd be left over? 0.5 of this guy. So there's your, what? Remaining 2-to-1, but that would only work if it went to completion. Because it's going to equilibrium, don't pick any of those relationships. That only works if it completely goes to completion. Because it's going to equilibrium, that relationship wouldn't work. So A kind of makes sense based on the multiple relationship. So it's a possibility if it went to completion, but it's not going to completion. So what's the best answer? Look at letter B. H2 is smaller than CO. H2 is smaller than CO. Would the H2 be smaller? Yes. Because of what? It's going to lose 2 compared to the 1. And then if you do the what? If you do the limiting reagent stuff, if this is 1 mole and this is 1 mole, let's change the color. And this is going to be minus 2x. That means it's going to lose all the 1 mole, right? So minus a mole, and this will lose a half that, correct? So that would lose 0.5. What's remaining? Wouldn't be 0.5 remaining for this guy? And what? 0 for that guy. Now it's not going to be perfect, but look at the choice, H2 is less than CO2, yes. It's not going to be a 0 to 0.5 because it's going to go forward, it's going to go backwards a little bit, but because we're adding so much extra, this is going to be smaller than that. That's the best answer. Okay, they love those relationship questions. I think on every one of these 3 tests, we've seen that. So the best answer, okay, is going to be choice B. The idea that something is going to be equal to each other doesn't make any sense. CO is equal to CH3OH. Let's see what that is. CO3 is equal to CO. That's not true because you're starting with what? This will be the excess chemical, right? So there's going to be always a lot more than that. So these guys can't be equal. That's why B is the best choice for number 22. All right, we used a different color. 23, and I know we're getting like punch drunk here with me talking, but hey, I'm tall. If we can get through the entire test tomorrow, that'd be a win. Okay, so maybe I'll go to 25. I mean, multiple choice anyway. Maybe. Okay, if I can do this. My computer is like too much data here. Okay. Nick was just doing the, what was that, the sprinkler dance? Okay. So number 23, once this cleans itself up.
No, get out.
Computer's some serious lagging going on. All right, one more time. All right.
Cool.
Not that cool. Okay. This question I remember going over with somebody. I've been here. Okay, so just get rid of this lag here. In number 23, a mixture of CO and H2 is pumped into a previously evacuated 2.0 liter reaction vessel. The total pressure of the reaction is 1.2 atmospheres at equilibrium. What would be the total pressure of the system if the... Okay. Okay, now it's happy, I think. Okay. Somehow I must have hit a button like 20,000 times. Okay, look at my kids at work, they're working the computer at home. It's not working. Okay, it's dealing with your 25,000 hits right there. Okay. Of course, I have 23,000 pages being printed. 23. Okay. So I'm going to mix these gases together. It's a previously evacuated 2.0 liter vessel. The total pressure of the reaction vessel is 1.2 atmospheres at equilibrium. What will be the total pressure if the volume of the reaction is reduced to 1 liter? So we're going to cut the volume in half. And this is Boyle's law, really, pretty much, right? So if the volume decreases 2 times to a half, we would increase the pressure 2 times, right? So you'd expect that if the pressure is 1.2 atmospheres, it would go to 2.4. But what do we know? If you look at the reaction, some of the CO and H2 are going to what? Combine to make less gas particles. So we can't expect the pressure to double. it would double if these guys didn't react, but the two gases, or in this case, I'm sorry, three gas particles making one would decrease that pressure below 2.4. It would definitely increase, but it'd be less, but it wouldn't be as great as 2.4. So I would say greater than 1.2, but less than 2.4. And the reasoning behind this is because some of it's going forward. Now, it might be less than 1.2 if the what? KC was huge, meaning we favor a lot less products. But the KC isn't huge. It means there's going to be some unreacted reactants there. So that's why I say B is the best answer. And 24. You know what? Last couple of tests I've been reviewing, bond energies have been jumping back up. And we should realize something about bond energies. Christmas. Bond energies, is this? No. Bond energies, what question am I at? This one, right? Okay. Bond energies. Now let's think about this for a second, because everything that we do in thermodynamics is products minus reactants. And it's on your reference table, the products minus reactants. But when it comes to bond energies, they do not have it there. And you have to remember that bond energies, okay, are related to delta H enthalpy this way. Enthalpy is equal to the bond energies total, so that should be the summation of the reactants minus the summation of the bond energies of the products. Now why? If I have myself a potential energy diagram, here are my reactants, here are my products. What did you learn? You should have learned that to go from reactants to products, you've got to break all the bonds first. And that takes energy. That's why my arrow is going up. So this is the energy to break bonds. That's what this arrow is, and that's what this part of the equation is. Okay, now, once I break the bonds, they have to reform into new ones. And anytime you make a bond, and I've mentioned this before, making bonds always does what? Decrease the energy. Remember this graph? Why is it dipped down? Why do we have a dip? Because the potential energy is dropping to make bonds. So when you make bonds, energy drops. And the difference of where you start and finish is delta H. What should the value of delta H be? Positive or negative in this case? Isn't it going up? Isn't it going up? The difference where I start and finish? So this has to be endothermic, positive. So if this is a bigger number, this is a smaller number, we want to go reactants minus products. So which of the following is true? So this is against what you've been seeing a lot of. People always mix this up. So the energy is absorbed as bonds are broken, correct? And in this case, it's what? Well, I don't know. Is it an endo or exothermic reaction? Delta H is negative, so I drew one that was opposite, my bad. So this is exothermic. So if it's exothermic, bad Grotsky, I drew an endothermic one. So let's do that. Okay, let's do an exothermic one. It looks the opposite. I guess I could have done that, but hey, I'm tall. We're almost done, party people, today. I'm almost done today. Okay, so we start in high and going what? Low. So it takes this amount of energy to break the bonds, and it takes this amount of energy that needs to be released. So the energy absorbed as the bonds in the reactants is greater. No, it's less than. See, this arrow is less than. The energy released as the bonds in the reactants are broken. Energy is not released when bonds are broken. It always takes energy to break bonds. Always takes energy to break bonds. The energy absorbed as bonds in the reactants are broken, correct, is less than the energy released. That's why C is the answer. Always takes energy, okay? And that's how that works. So C is the answer. Okay, they just brought back something. And I really feel like in part 2, on Monday, you're going to see bond energies broken minus bond energy formed, okay, somewhere. Okay, so here's the last question that we'll do today. Yes?
You need to absorb energy to break a bond.
Always, because bonds always have lower energy. Bring back this diagram, right? When they bond, the things dip. They make a Spencer, right? Why do they dip? Because we're forming a bond. So therefore, to get it back up, you need energy.
He left like an
He's
hour
left?
ago.
Yeah, yeah.
A while ago.
He wasn't here.
No, he was
Okay,
here for like
25.
5 minutes.
A solution is prepared by adding what? look at this, party people. I've got a weak acid. Imagine that, an acid and base question. With what? A strong, what is this? This is the salt of the conjugate base. What are we making? A buffer. 2 ways we make buffers. You go, girl. Okay? 2 ways you make buffers. You can half titrate a weak acid, or partly titrate, doesn't be half, or you can add what? The conjugate base in the form of a salt. So I'm adding HC2H3O2, that's the acid, conjugate acid, and I'm also adding indirectly C2H3O2, and that's negative. This breaks apart to Na plus, it spectates. So I've got my base and conjugate acid. I can't say this enough, and I've been saying it over and over again. They love buffers. You'll see 3 or 4 questions on buffers. How do you identify a buffer? It's a conjugate acid-base pair. They are not 2 different chemicals. They are the same chemicals, and you should know why. The Ka and the Kb are what? Inversely related to each other, right? As one goes up, the other one has to go down. So these guys cannot neutralize themselves. So anytime you've got a buffer, it has to be the same chemical plus or minus an H. Now in the question, they said they're adding 3 drops of Jupiter here, and in this case, they're adding what? Strong acid, which dissociates into what? H+. And they want to know what the reaction is. Now we know that the pH is not going to change much, right? We have a lot of acid, conjugate acid, a lot of conjugate base. So, what's the reaction? Well, because we're dropping strong acid, isn't it going to react with the what? Where is it going to react with? Right. Isn't the conjugate base going to neutralize it? The pH isn't going to change much because I have some conjugate base sitting there. So what's the reaction going to be? The reaction is going to be a buffer with the same chemical. This is not a buffer. This is not a conjugate base that has any ability to do anything with water. This is not a buffer. Okay, what's our buffer? That's what happens in water. We have the same acid and same base, so C and D are your best choices. But what did I just say? We're adding drops of Jupiter. In this case, the Jupiter is the H+, reacting with the what? Reacting with the base to reform the conjugate acid and making water, neutralizing it. That's why C is the answer. Okay? So I'm going to finish up there. I think 3 hours of this is enough. What I really suggest for you guys, take a test you've done already. I bet most of you guys got plus 20 wrong in multiple choice, and that doesn't mean that's a bad thing. Take one of these tests again. See if you can recognize the principle behind it. Oh, how did I get that wrong? I don't care if you see a question, oh, I know the answer already. There's going to be questions you've forgotten. There's 150 multiple choice questions in this new format. You go over every single one of them. I'm going to review 26 through 50 on this test, so if you want to go and do something else, you can. Okay? Anything else you want to make, email me. If you want a crash course in a certain area, email me. I'll make it. I'll do whatever I can. I'll be here Friday. But if you want a crash course tomorrow in rate law or something like that, let me know. Okay. I know she just went to bed an hour ago. So these are tests you've already had. But this is practice test 1. This was the final 3, and I think we're working on, or this might be 2, I told them. But in any case, this is the one I'm working on for class. You have all 3 of those? It may be nice, maybe 12 kind of way to have them. All right, so we're going to move forward here and go through this part of the multiple choice. as I keep saying, I've been harping, even though I don't play a harp, on this, because if you can get through the multiple choice covers the entire curriculum, okay? And what you see in multiple choice, you're gonna see in part 2, okay? You just gotta keep hammering on it. I'm a big believer of that, so hopefully you've been doing that and spending time with me online. Sounds kind of creepy, but let's continue. So in 26, the reaction represented above, this is, again, the multiple choice of the 2014, or I should say practice test, whatever I call it. Yeah. So in this reaction, what do we have? We have the number of permanganate ions that must be equal to which of the following. Okay. So in the reaction represented, the number must be, well, okay, so we've got a 1 in front, nothing in front implies a 1, okay? And so what are the ratios here? So it's going to be something to something. So if I look at my choices, in the reaction represented above, the number of permanganate ions that react must be equal to which of the following? Well, if I look at iron plus 2, and there's a 5 in front, all right, it's a 1 to 5 ratio, so this has to be 1/5 of the iron, okay? And that's all that really that problem is. Yeah, that's a 2000 right there. You can pick that one. So there isn't much to talk about here other than realizing that this is basically straight stoichiometry, and we're dealing with a 1/5. So this is 1 and this is a 5, so the ratio is that 1/5. And if you're ever to do a type of question that is going to pop up in this multiple choice, as with most tests, you're going to see a limiting reagent problem. You know, like for instance, if they were to give you 20 moles of iron plus 2, and they were going to give you, let's say, 20 moles of both, and you said who the limiting reagent is, knowing it's 1 to 5, I kind of start with the big guy, the big number here. This is going to represent what? All of it, right? So that's 5. So if this is the 5, then I need only what? 1/5 of that. So 1/5 of 20 would be 4. So you would use only 4, and we would use all 20 of these, and this would be minus 20, and this would be minus 4, and we can clearly go fast and say, okay, in this example, iron plus 3 is the limiting reagent, okay, because of the 1/5 as much. So that's all that is. The other choices here don't have the right ratios. 1/2 the H2Os, I'm not sure how that would work as 4 there, and the other choices B and C make no sense because they have the ratios mixed up. It's not going to be 8 times a number, it's going to be 1/8, okay, and then not 5 times, it'd be 1/5. So that's how that would go. All right, so again, if you were to, if you still don't see this, and I think most of you guys do, okay, getting rid of the permanganate, you would have 1 of them for every 5 irons. If you're doing stoichiometry, you'd put the permanganate on the bottom so that it would cancel, okay? And you can see that this one's going to be, if you're going to go to iron, 5 times as much, and if you're going to go backwards, it'd be 1/5. I think I've talked about that enough. So 27, take the easy questions where you can. All right, so I'm just jumping all over the place. So 27, we've got a graph of absorbance. If you haven't already figured out, they love spectrophotometry, okay? So they got concentration. For those that forget, you've got this cuvette, right? This little plastic little guy, and we're putting something that has some color in it for all the reasons we've talked about this year. And if it's got color, we shine some light with a certain brightness through the cuvette, through that path length, and there's a detector, and that detector basically measures what's the missing light, okay? And the missing light is due to what the chemical is absorbing. So as the absorbance goes up, the concentration goes up. We also have this little formula that's been popping up. A equals A, B, C. What this means is the absorbance, the amount of missing light, because the chemical is absorbing it to get excited, or in this case, to give off a color because absorbing wavelengths of light, is equal to that absorbance constant times the path length that we used, 1.0 centimeters. That's the length through the cuvette, and this C is concentration. So clearly, as concentration goes up, there's going to be more missing light because there's more chemicals to absorb it. So in any case, a little quick review of spectrophotometry. I'm having a tough time scrolling down. So they say they prepare 5 solutions of copper sulfate, different concentrations, filled 5 cuvettes, la 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 la, and they get the data above, which you can clearly see is rising, okay, as the concentration goes up. Now, you'll notice there's one data point that's not really following the trend. It's an outlier from the other data points, and they're asking you what's the possible scenario for that. Since we've done the lab in many ways, this should not be a big deal, okay? What's the scenario? Well, the cuvette into which 0.600 molar solution was placed had some water droplets. Now, if there's some water droplets, would that diluted or concentrated? Diluted, which means the absorbance would be higher or less? Less, because if it's A equals A, B, C, there's less concentration if you had some water, so the absorbance would be lower. So A makes no sense. Okay, the cuvette into which you add this was filled more than the other cuvettes. Having more of it, does that change the concentration? No, the molarity is going to be constant, the volume is going to increase. Yes, there's more moles, but the concentration per volume stays constant. So that wouldn't make any sense. The wavelength setting was accidentally moved away from the maximum absorbance, which means you would actually have a lower absorbance. If it's stuck on a higher setting and you lowered it, you would get a lower. Remember, that point is above the line. So process of elimination, D is the answer, and D is the answer because the cuvette used had not been wiped clean. Maybe their fingerprints were on the cuvette, which means a light had to pass through what? Not only the solution in the cuvette, it had to pass through whatever oily film you had, okay? So there's more missing light because there's more stuff to go through, including the dirty cuvette, and that's why you had a higher absorbance. But in any case, that one is D, all right? Again, they love the idea that we are using spectrophotometry. I would think you're going to see a question, mass spectrometry. We did not do, but we definitely talked about it and looked at it. Okay, rate law. All right, 28. Reaction is experimentally determine the rate law above. So we have the rate law to be first order. There's nothing in front, so first order it is. A chemist proposes 2 possible mechanisms, which are given below. Based on the information above, which of the following is true? Now, the first thing I do with mechanisms, and sometimes they do this in part 2, is they want you to stoichiometrically prove that's a possibility. Now, what they want you to do there, and even though they're not doing it in this case, it's a good idea to do this because if they're trying to pick between mechanisms, there might be a mechanism that doesn't balance off to the overall. So it's really a good idea to see if, in fact, both of these will, when you cancel out all the either catalysts or the intermediates, that they will equal the entire compound. So you can see that this is 2x, this would be an x, and this x would go bye-bye. This intermediate would go bye-bye, and you can see that we're left with the exact reaction we have up here. And if you were to do the same thing over here, 2x, 2x, let's see here, xy, xy, and then you have y, why not? Okay, and then we have, what other intermediates am I missing? Okay, this guy. So we can see that in both examples, both of these, okay, stoichiometrically come out to the overall. And sometimes in a rate law problem, even though this one is not asking for that and it's not applicable, okay, I'd like to go over those things. In a part 2, they could say, hey, prove that this is the rate law based on stoichiometry, and all they're asking you to do is to cancel out to the overall. All right, so in this case, they both do that. So that's not the issue. So the issue is, if it's first order, how in the world do I realize which one is first order? Okay, well, if I look at the mechanism 1, I'm going to get rid of this canceling stuff here to make my life simple, although it's very complex. Okay, not as complex as Alex, but in any case, all right. If you look, what would give me first order? First order with respect to x2. Notice y2 is not in the rate law. Why? Enough y jokes. But
Probably.
that could be, but Better yet, it maybe has a rate order of 0. So it's not given. If it's a rate order of 0, it has no effect to the overall mechanisms because it's not in the slowest step. So both of them are not showing Y2 in the slowest step, which is a good thing. If something is a 0 order, they're not going to write it because it's not in the slowest step. You still need it. So both of them show that's a good thing. So the slowest step just has the x squared. And because this is called an elementary step in a mechanism, the step that is called the rate determining step is the slowest step. And that is called an elementary step. We get our rate law directly from the slowest step. And coefficients are never going to be the exponents unless we know the reaction is a single step. Since this entire rate law is based on this single elementary step, okay, then we can use this coefficient of 1 for both of them and make it into the order. So again, both of these mechanisms are showing the slowest step, only having x2, not y2, because y2 is a 0 order, it's not written, so it's not part of the elementary step that basically the whole mechanism or reaction process depends upon. So I find the slowest step, I use the coefficients of the slowest step because it's elementary. Both of these are applicable. We can't know definitely which one, but we can definitely say that both are possible. So both mechanism and 1 and 2 are consistent with the rate law. Why? Because the slowest step has the coefficient of 1, and the y2 is not in the slowest rate determining step. Okay, moving forward, 29. Now this one, a lot of people got wrong. Okay, these little diamonds here, multiplication here. Now this is a great little question because I'm seeing this pop up often again. I want to remind everyone that when you have reactions that just like we did above with a mechanism, when you have an overall reaction, the overall equilibrium constant is the product of the individual K's. You say, well, Mr. Grotsky, where did we ever do that? Well, we did do that in derivation. I showed you NH3 in water. That's a weak base that pulls an H away from the water, ionizes it, makes the hydroxide, and it makes the NH4 plus. And this would have a Kb. Then I took the conjugate acid of this and had it in water, NH4 plus in water. And what did it make? Well, this gave an H, it's a Bronson-Lowry acid, so this becomes H3O plus NH3. And this would be the Ka of the acid. And you notice, when I cancel everything off, what am I going to get? Okay, I'm going to get two waters doing what? Breaking apart into the hydronium ion, the acid part, and the hydroxide, which by the way equals what? What is this reaction? Kw. And what we learned? Kb times Ka equals Kw. So I did teach you that equilibrium constants of individual steps will equal the overall when you multiply them if they what? If they cancel out to the overall process. That's important. That does pop up. Equilibrium constants are multiplied together. It's kind of like a little Hess law with them. All right? So let's get rid of this, okay, and talk about what the problem's all about. I'm not sure why I got rid of that, but I am told. Now, question is, what's the overall? The overall I have to look at very carefully. Notice there's two HFs. There's only one HF here. Okay, there's two H pluses, only one H. Okay, for these F negatives to cancel, doesn't this have to be a 2 here? So really I have to do what to the second step? Multiply by 2. I had to realize that. Now everything's going to cancel, and I have the overall reaction. So notice, this K2, the equilibrium constant, was based when these coefficients were 1. That's a big, big understanding right there. Okay? This equilibrium constant was 1 times 10 to the 3 when these guys were 1. Let's just, for fun, it is a lot of fun, to write the equilibrium expression for this reaction. It's going to be the product, HF, okay? It was to the first power, and it was F negative to the first power times H plus to the first power, and it equaled this number, okay? Now, when I times everything by 2, now the coefficients are what? Right. Now they're squared, correct? Coefficients become exponents. So what is this number, 1 times 10 to the 3? It's really, what's the number there? Yeah, it's 1,000. So let's write the 1,000.
Thanks, Sam.
Feel free to.
Oh, hey.
So we've got our K2 equal to 1,000. Now I'm going to try to make some sense to this for me. I'm going to make this equal, okay, to 1,000. And one way I can do that is what? Make the top number 1,000 to the first power, right? And the bottom number is equal to what apiece? 1 apiece. I'm just going to make my life easy. So that's a fictitious way I can make 1,000 in my head. Because I got to understand this. Now, what just happened though? By timesing this by 2 and the coefficients becoming 2, now everything is what? Squared. So this 1 squared times 1 squared, that's pretty simple. What's that? 1 times itself. Put that in your calculator. And this squared is, well, 3 more zeros, right? So this is 1 times 10 to the 6th over 1. Put that in your calculator. It's 1 times 10 to the 6th. So K2 becomes 1 times 10 to the 6th. Okay? And now what we're going to do to get the overall is multiply. We're going to multiply K1, which is 2 times 10 to the negative 6. And I'm going to times that by my K2, which is 1 times 10 to the negative 6. Okay? That's all I'm doing is multiplying my K's. Now that I know my individual K's.
Positive 6 for the second one.
Okay, yes, sorry, positive 6, thank you. All right? So when we multiply numbers with exponents, what do we do with them? Add them. So 6 plus a negative 6 gives me 10 to the, which is 1. 2 times 1 is, so K1 times K2 equals K3, which is equal to 2. Is 2 greater than 1 or less than 1? It's greater than 1, which means the products are favored, which means you have products. So back to the choices. I know K3, okay, is greater than 1. And I know it's thermodynamically favorable. Why? Why do I know it's thermodynamically favorable? If products are favored, that means it's going forward to produce products. Absolutely correct. You have to understand, when your K is bigger than 1, your delta G becomes more negative. Okay? We used this formula way back when. Delta G, okay, is equal to what? Negative RT ln of what? K. So as the K becomes bigger, positive 1, it maintains this negative. This becomes more negative for the forward direction. Okay? All right. A lot going on there. A lot of people got that wrong. A lot of times, guys, they'll give you questions where all you've got to do is multiply your equilibrium constants. But this was a nice little spin. Remember, this was a question that was designed for you to get wrong. And if you did, so be it. If you understand this now, great, because if you see a question like it in part 2, maybe you can handle it. There's a lot more to get right. You get this one wrong, I can see that. A lot going on here. Okay? Moving forward. Maybe. Okay. This one you should not get wrong. First of all, we're talking about H bonding here. Little AP Bio questions sneaking in. Okay, AP Chem, liking it a lot. okay, nitrogenous bases on the DNA backbone. Not feeling the love like I thought I would feel about it, but hey, all right? All right, now listen, H bonding for the millionth and one time only happens with FON, fine. Following H bonding. Now why? These guys are electronegative enough, they're the most electronegative atoms. They have the greatest effective nuclear charge for their atoms and their sizes. So because of that, what they do is they pull that pair of electrons between the H and one of these guys so close to it, what it does is it dangles what's left over. And what's left over, okay, when you pull that pair of electrons away from it so much, is just a proton. A hydrogen is one electron, one proton. So if these guys are really small, what you have is a proton dangling out there. And that becomes very positive. All right, let me just get rid of that drawing because it's not going anywhere good. Now, that being said, let's look at our choices. Which one is showing correct H bonding? Is this an electron deficient H? Carbon and hydrogen have almost the same electronegativity, so that would be incorrect. That would never H bond, that's right. Okay, ours is second bond. B, let's see what we got here. Another non-what? Electron deficient H. That's not an FON. That's not going to H bond, not going to happen. Okay, B goes bye-bye. Looking at C, okay, I've got another non-electron deficient H here. This is not going to H bond. It's not going to dangle that proton out there. They're sharing electrons almost equally. So process of elimination, D is the answer. And you can see that this N, which has a little bit positive because of that proton dangling, is hooked up to an N. And this also bonded to the N. So this is the H bonding that's correct. Okay, so duh, D is the answer. All right, easy question in my opinion. Okay, here comes what? Ooh, positron emission spectroscopy questions. You're going to have these peaks. You're going to have what? Binding energy. All we're doing in this type of a question is we're taking a sample. Okay? Basically, using the photoelectric effect, we're shooting X-rays at the sample. High energy photons. Some electrons are emitted. Okay, so electrons are emitted. Now you should know why they're emitted. If this is the energy of the photon. Okay, there's two parts. There's the binding energy that we overcome, and the rest of the energy is to do what? Measure the kinetic energy of the ejected electron. So what we do is measure the kinetic energy in photon emission spectroscopy. We measure how much by how many, okay, by the way we use a charged tube. Okay, I love explaining this because understanding how it works really makes you understand the question. These are negatively charged tubes, so the electron repels them. And the ones that go faster, okay, are not affected by the charged tube as much, and they can hit a detector. The ones that are going slower are repelled more, and they don't go as far. And we can measure how many of these are hitting the detector and the relative distances. But the bottom line is, the faster we go, the higher the kinetic energy, right? The less the binding energy. Okay, so if I've got something with a lot of kinetic energy with the same photon, the binding energy arrow's got to be less. So essentially what we're measuring is how much energy to separate these electrons. Okay? And if you notice, binding energy usually increases as you go this way. So this peak, which is showing a lot more electrons because it's higher, is showing a much higher binding energy. Which means these are electrons that are held what? Closer to the nucleus. This peak showing a lower binding energy for another 1s, they're telling you this, is probably held much farther. Easier to remove electrons in shells that are what? Farther away because they feel the electrostatic attraction less. So that's all that was. I know you probably didn't need the full explanation, but hey, I'm tall. All right, 31. So a sample of carbon and fluorine was analyzing using the X-ray photon emission spectroscopy. The portion of the spectrum shows the 1s peaks for both. Which of the following correctly identifies the 1s peak for the F atoms? All right, we should know in our reference tables, okay, somewhere I don't have my reference tables out, but in my reference tables, I know that fluorine, okay, is over to the right, right? And we have, let's say, a boron, carbon, nitrogen, oxygen, and fluorine in the second row. And then, of course, we've got our neon at the end. Okay, this is atomic number 9, atomic number 10, atomic number 8, 7, 6, and 5. And what do we know in the same, if you're in the same principal energy level, same row, it's all about the nuclear charge. So fluorine's got more protons in the same energy level. It's got a higher nuclear charge, higher effective nuclear charge. So therefore, it's going to be a lot tougher to remove what? Fluorine's electrons at the 1s level. So we would say, which identifies the peak for the F, we would say peak X. This is peak X right here, okay, because F has a greater nuclear charge than carbon, and therefore the electrons are held tighter to the nucleus. And that's the reason why fluorine has a higher, by the way, ionization energy, okay? So that's why answer to 31 is B, okay? Greater nuclear charge, all right, or effective nuclear charge, however you want to talk about it. Okay. So 32, one of those questions where it's, you'll see definitely something like this Monday where they're going to give you definitely a group of questions on one area. Okay. In a titration experiment, H2O2 reacts with aqueous permanganate. Okay, dark purple is added to a beer of colorless acidified H2O2. La 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 la. Now, endpoint is that pale pink color that we actually did. And now, great little question here. At a certain time during the titration, the rate of appearance of O2. Remember, the rate of reaction is equal to either the appearance of the products or the disappearance of the reactants. They could be both related, all right? And that relationship, very important because this pops up all the time. That relationship is stoichiometrically related based on the what? The coefficients. So, at a certain time during the titration, the rate of appearance of O2 was 1 times 10 to the negative 3, 0.001. Okay, what was the rate of disappearance of MnO4? Negative, at the same time. Okay, well, what's the ratio? Well, the rate of appearance of O2, okay, is 5 moles. The rate of disappearance is 2 moles. So what do you know? What do you know about this? What's the ratio? Right, so permanganate is it loses 2/5 of what O2 gains. Now if you don't see that, okay, if you don't see that, if we're relating it back to O2, you can do this. Okay, 1.0 times 10 to the negative 3, we all know it's 0.001. And this is O2, right? Watch how I relate this. I want to get rid of my O2 to get my what? Permanganate ion. And what's the ratio? 2 to 5. Do you see how I'm grabbing that? Some people can see it right away. But if you're doing this, if you have the rate of appearance of the oxygen, now you're going to have the rate of disappearance by the permanganate. So all I got to do is times this by 2, very simply, and I get clearly, hope we can do this answer, this is 0.001. I know we don't have a calculator, but you can do this. So this becomes what? 0.002, right? This is 0.001. I'm timesing it by 2, okay? Now I'm going to divide it by 5. I need a calculator. No, you don't. Okay, isn't this really 20 divided by 5? Yeah, now it's not going to be 4 here, the 4 is going to be over here, correct? So that's going to be equal to 0.00, because this was 20, 04. That's it. Which is the same thing as 4 times 10 to the negative 4, which is choice B. So yeah, I know we don't have calculators.
Just D.
What's that?
Just D.
It is D because I can't read. I want negative 4. Okay. Thanks for helping me out there. So yeah, 4 times negative 4, I just can't write the same answer. All right. So rock on. Okay, so yeah, so you had to do a little bit of stoichiometry. Really helpful to see what you're relating it to. They gave you information about O2, getting the permanganate, and just doing the simple math. They're never going to give you crazy math numbers. Okay, 33. Which element is being oxidized during the titration? Okay, now what is oxidation? Leo the lion says grrr. Okay, so if we're going to do this and wipe this out, wipe out. Okay, now Leo the lion says grrr, so gaining electrons is reduction and losing electrons is oxidation. Why did grrr first is beyond me, but hey, I'm tall. So we need to find who is losing. If you're losing electrons who are negatives, that means your charge is going up. Now if you're not sure, okay, you can just do trial by error. Mn is +2. Evaluate your MnO4. This is an important skill. It keeps popping up. This whole thing is -1, so I do bottom numbers -1. If the whole thing was 0, bottom numbers have to equal 0. So here's what I'm going to do. There's 4 oxygens. I know that oxygen loves to gain 2 electrons, become -2. If I look on the periodic table, I see O, I see F, and I see neon. That tells me that oxygen likes to gain 2 electrons to become stable like neon. You're not going to see oxidation states listed on your reference table. Feel bad, now I'm over it. So -2 individually times 4 is -8. This has to be +7 for the manganese. +7 going to +2. Hey, +7 going to +2 is going down. That must mean you're gaining negatives. That's reduction. So that means that permanganate is out. Now, I'm looking at the O. What's the charge of any standalone element? Rhymes with 0, exactly.
0.
0, perfect. You guys are rappers. Okay, now, I see O going to 0. So let's check out O in what? Hydrogen peroxide. Now, some people like to remember, I can't speak, remember or memorize that in a peroxide, oxygen is -1. I don't think it's necessary. Hydrogen only has 1 electron, so it loses 1 to become +1. There's 2 of them overall, so it's +2. The bottom number is 0 in this case because it doesn't have a charge. This has to be -2 overall due to all of the oxygens. Each oxygen is -1, and there's our answer. An O -1 becoming an O0. My charge is going what? Going up because I am losing electrons, and I put that 1 electron here. So they're looking for oxidation where I'm losing electrons. Notice I put the electron on the product side so that both sides of my half reaction have a 0 charge. Notice they weren't asking for a half reaction. I'm just giving it because I'm showing off. So it's going to be the O -1 to O0, and that's why A is the answer. Or if we're learning this, okay? 34. Which of the following best describes what happens to the pH of the H2O? I can do this. Okay. Now, what's happening to the pH? Well, what's happening to me here? I can't move this baby. Okay. So what's happening to the pH? Well, as the reaction proceeds, I notice that, yes, I'm producing some water, but more importantly, aren't I losing my protons? Aren't protons being consumed? Yeah, so therefore, if I'm losing protons, the pH is going to do what? It's going to rise, right? So the production of the water, nah. H2 charge, nah. The H+ ions are consumed, right? We're losing our protons. So therefore, the pH has to rise. That's your best answer. Okay, so the solution becomes less acidic. 34 is cut, a C. All right, 35. The BF3, it's the best friend, multiplied by 3, I guess. Molecule is non-polar, whereas the NF3 is polar. Which of the following statements accounts for the differences in the polarity? My gosh, look at the answer. Look at the choices here. They think you know nothing. They do. They think you know nothing. In NHF3, each F is joined to an N with multiple bonds. Why would a multiple bond affect the polarity? It's got nothing to do with if you got a singular polar bond. It's got to do with the what? The three-dimensional arrangement. Okay. So we're getting rid of NF are polar where these are non-polar. Well, that's not even true, but even if they're polar or non-polar, it's about the three-dimensional arrangement. There are scenarios where things that have non-polar bonds only and can be polar because of their what? Three-dimensional arrangement. Ozone, little fun fact, has all what? Non-polar bonds, but because it's a bent molecule, that creates polarity. Too much info, I know. NHF3 is ionic. Non-metal. Okay. So D is the best answer. Unlike BF3, NF has a non-planar geometry. Now, I want to kind of just do this real quick because it could be a part 2 question where they say draw it or prove it to me. So whatever is on multiple choice is certainly game. Okay, just like, I don't know, ducks in a pond. But the point is, NH3, NF3, not your best friend 3. What does this look like? Well, N has 2 lone pairs, and then you have the F. What is the hybridization here? What is the hybridization here? sp3 with a lone pair. This lone pair does what? Pushes these bonds that were in a nice tetrahedral formation downward into what I said, basically into this what? Top of a 3-sided pyramid. So we go triangle pyramidal. So this is a top of a 3-sided pyramid. And these H's are being pushed downward into an asymmetrical shape. Very polar. Now we've got BF3. Now boron only has 3 valence, so you're going to make 3 F bonds. This, of course, is sp what? Thank you for saying quietly sp2. Someone was thinking it. I have my 6th sense working. There is 1, 2, 3 pairs of electrons around the central atom. That means an S and 2 P's came together. Okay. Now, what's the shape of this? This is triangle planar, right? This is sp3 because we have what? 1, 2, 3, 4 pairs, and this would be the tetrahedral shape with the lone pair. We consider just that area. So this is planar. The reason why this is non-polar is because, as I love to say, it is equal in its unequalness. So it has 3 polar bonds, but they're equal in all direction. I know I overtaught that, but these are things you can see in pot 2. Number 36, classic question. Classic. You will see Q versus K in so many different ways. This one is an obvious question. So at a certain point in time, a 1-liter rigid container has these amounts of moles of gases. Okay, now you notice it's in 1 liter, so I can get molarities pretty simple. The molarities are the moles because mole over liter. Which of the following describes how the measured pressure in the reaction will change and why it will change? Well, we have to know what the Q is. They're telling us this is a reaction quotient. This is some place in time where we have these. And as I always love to draw, this right here. Here is my K. I don't care if it's KC, KP, KP, KA, KB, KW, AOK. It goes right here. Now, what's the Q? Well, Q is equal to products over reactants, coefficients become exponents, solids and liquids don't apply, they're all gases. So what's my Q? My Q is going to equal to my product, PCl3, which is 1.5 to the first power, over the reactants. The reactants is PCl3, which was what that was. Thanks for correcting me. Okay, so this is, let's just write it out because I'll make mistakes. This is PCl5 over PCl3 times Cl2. Now that I've slowed myself down, okay, let's put the values in. All right, to my Q. So PCl3, as I said before, PCl5, where are you, is 2.5 molar. Mr. Grotsky, it's moles. How do you do molar? Well, it's moles over liter, so it's the same thing. So 2.5 goes on top. On the bottom, I have PCl3, and that's 1.5. And I'm timesing it by my Cl2, which is 1, to make some tough math here. So 2.5 divided by 1.5 times 1, hopefully everyone will see it's 2.5 divided by 1.5. Now, I can't do this in my head. You don't have to. All I gotta know if it's bigger or smaller than K. By the way, what would be, if this was 2, wouldn't this be what, 3? Right, so the Q, by estimation, is some number between 1 and what? Or 1 and 3, right? 1 and 2. Somewhere between 1 and 2, I can do the math. So the Q is equal between some number between 1 and 2. What's the K? 6.5. So the Q is some number between 1 and 2, which is what? Q is less than K. It's going to go forward. Now, if it goes forward, look what we have here, party people, for the millionth and one time. We have what? 2 gases combining to make 1 gas. So because it goes forward, not a tremendous amount, but as it goes forward, we're going to lower the pressure because we're going to lower the total number of gas particles, and pressure is due to gas particles. So the pressure will decrease because Q is less than K. I have seen this problem, something like it in many different fashions over and over again. Something to definitely cash in cha-ching. Okay? Full of sound effects.
Honestly, when this backfired.
Okay. Now, let's look at this problem once I get rid of this stuff. Maybe. Looks like my computer's not happy. Could be the 25 tabs I have open. Okay. So I've got a reaction. Oh my God, so much information. So much information. I'm giving up already. No! Consider the reaction represented above. When equal volumes of N2 and H2 each are at 1 atmosphere, are mixed in a closed container, there's absolutely what? No NH3 being given off. What does this tell me? The reaction's not going forward. Why is it not going forward? It's no. Look at the spontaneity. Delta G is negative. Spontaneity has nothing to do with the rate of reaction. How fast the reaction goes has nothing to do with how negative delta G is. This is spontaneous. It is very negative. But what do we have with all reactions? Okay? We have, this is an exothermic reaction, correct? So if I was to draw a potential energy curve, it would look something like this. High going to what? Low. What is preventing my reaction from going? This little bump here. The activation energy. We have gasoline sitting in a container. Doesn't it like to react with oxygen and burn? Absolutely. Is it reacting? Probably a little bit, but not enough. Okay, it's just sitting there until you add the what? The spark.
This piece of paper.
Okay, to overcome. All right, so the reason why your papers aren't burning right now is because of that. So all that question was that a high activation makes the forward reaction extremely slow. It's about the activation energy. Okay? And we all should know when R, this is a little aside, R equals K times the, let's say the reactant, A, whatever it might be. This equilibrium K is tied to something I like to call activation energy. We write in big boy and big girl chemistry as E of A. So the higher the what? Activation energy, lower the what? The K value. Okay, that's called the Arrhenius question that we looked at. Not needed to know that, but you should know that, okay, in terms of that relationship. Okay, that was a lot of fun. Oh, yes! You bet I love the titration. Yes! What do they want? They want the pKa of the acid, and they want the concentration of the base. So they want 2 things. they want the pKa, or we say pK, and they want the concentration of the hydroxide. Now, what do we have? We have some acid, okay? Data collected. Notice we're adding what? Look at this curve. What are we adding to what? pH going up or down? It's going up, so we're adding drops of Jupiter. In those drops, what are we adding? Right, so we're adding hydroxides into acid. Great. However, in this experiment, we already know the concentration of the acid. They told me the acid is 0.1 molar. And they told me that the solution is 20 milliliters. Okay. What's the concentration of the base? Where is the equivalence point? Find your asymptotic line. Don't be an asymptote. Find the asymptotic line.
It's basically 20.
And
20.
yeah, I would say right there, so it's basically, for the pun involved, good job, you get 20 milliliters. This is a tough problem. Check it out, party people. I have 20 milliliters of a certain concentration of an acid. I need exactly 20 milliliters of the base to neutralize it. What could be the concentration of the base? Yeah, I'm throwing my entire career out there and saying that it's 0.1. Okay, now if you like MV equals MV, I'm not a big fan, you could have solved for that. Or if you wanted to, because you don't have a calculator, use the math, you could have said, okay, 0.020 liters times it by what? 0.10 molar. Liters times molarity always gives me moles. I get point what? 0.002 moles. And then you divide that by what? The volume of the base that was added, which is what? 0.02. And you could see the math is pretty simple. It's 0.1. Or you could have recognized that right away. So that's the first part. Second part, how do you get the pKa? Well, here's the buffer region. If it took 20 milliliters to what? Titrate it, halfway titration is what? 10. Now, why am I doing this I call max buffer position? Because I have equal amounts of what? I'm going to have my weak acid, I'm going to produce my conjugate acid. If I half titrate the acid here, I'm going to have equal amounts of these guys. Okay, you should know this. This is my third practice test I've gone over this way, so I shouldn't have to explain it, but if this is the first one, okay, you have to know that when you half titrate something, that means I had what? I did not add enough what? Base to neutralize all of this, but whatever base I did add, forced the production of the conjugate base. Alright, since if I was to make this 2 moles of acid in my beaker, and I added 1 mole, you can all see this is a 1-to-1, all right? I would lose 1 mole, and I'm left with what? 1 mole left. This would go bye-bye, and I'd produce 1 mole of this with 1 mole of acid. So what does that mean, party people? That means that when I use the Henderson-Hasselbalch, and I'm sorry if you understand this 5 minutes ago, but cool if you do. Henderson-Hasselbalch's pH equals the pKa for the millionth time and 1 time. Log of the conjugate acid, A minus over what? HA. This is going to go to 0 because if I have equal amounts of these guys, okay, at the half what? Half neutralization point, the log of 1 is 0 and my pH equals my pKa. All you do from that max buffer position, I know I'm not drawing a straight line, but try to find that value. Okay, what's that pH there? So, my gosh. So our pKa is 4.7, and that hard math problem, the concentration of the base is 0.1. You'd be surprised how many people get this question wrong. Okay? And how many times have you seen pH equal to pKa if you're doing what I asked? Okay, whoa, heating and cooling curves. Okay, this is back some basic chemistry, although there's no acid base here. Now, this question is all about conversions. This is all about conversion. This is a conversion question. Part 2, somewhere in your part 2 or your multiple choice, they love to do conversions. So what they said was, how much energy is required to melt 64 grams of methane? 64 grams of methane. Now you needed to realize that this is heat of vaporization. I just burped and I think hiccup at the same time, so it's kind of weird. So that's called a hic burp. I'm not sure. In any case, all right. You're laughing at my social incompetence. I'm sorry. I made a scene. All right, now, so heat of vaporization, heat of fusion. This is melting. This is solid, liquid, gas. Crazy amount of energy. So this is solid going to a liquid. This is melting. They gave me 64 grams of methane, party people. Look what they give me. Look at the units. This is kilojoules per mole. So I got to convert this to mole. Hello. They were nice enough to give us, methane is CH4. Methane, they gave us that the formula mass of methane in the problem was what? 16. I don't know why they did that. I think we know that because we go to the molecular mass party and memorize these. But hey, if you missed the last one, you're lost. So there's 16 grams per 1 mole.
I can't do this math.
Yeah. 64 divided by 60. You got it 4. Okay, you used a calculator. I saw you. You had the Apple. You had the Apple Watch.
You're a cheater, Sam.
Oh, I would have pineapple.
Sam doesn't even have an iPhone.
That is not true. 16 times 2 is 32. 32 times 2 is 64.
Sam told me. Yes, 16 times 2 is 32.
Sam
Yeah.
couldn't even have an Apple Watch. He has a Samsung.
Oh.
Oh, what is happening?
I guess Apple's a line of rubber on blue. I don't know. That was a great comeback. Okay. So we've got 4 moles.
That's like normal. That's like normal for our class. I'm making these kind of jokes.
So 4 moles. My gosh, what is the number? It's 0.94 kilojoules per 1 mole. So I'm going to, just because I'm cool and tall, I can know that this is almost 1. Isn't this almost 1? And if you ask Sam, he'll tell us 4 times 1
What is it, Sam?
is about 4. And I say about 4 because it's this. And it's kilojoule. Okay? So the only answer there, okay? Now, of course, only answer there, it's about 4 is choice B, 3.8 kilojoules, okay? Because I'm getting emails from students, I can't do the math with the calculator. Slow yourself down, round off. Look at these numbers, are so far apart from themselves, we can do what? We can estimate. So that was a converting problem. Number 40. Which of the following best explains why more energy is required for the process occurring at 110 Kelvin than the process occurring at 90? Well, if you don't remember, at 110 Kelvin, we've got a liquid go into a gas. Okay, tremendous energy right there. So the problem is that we've got a phase change, heat of vaporization. And what we're doing is, in order to become a gas, the liquid molecules' intermolecular forces have to be totally overcome, because gases, especially if they're acting ideally, like Tahira, is that we, okay, a little shout out to my videos here, we need to overcome these to become a complete gas. So you have to overcome what? Intermolecular forces. Okay? So the intermolecular attractions are completely overcome during now, are they?
Please do that.
Almost. The solid phase, they're weaker. No, they're stronger in the solid phase. Electron clouds of methane are less polarizable at lower temperatures. That's crazy. And vaporization involves a large increase in temperature. This would be nice if it said large increase in what? Energy, right. Temperature Q is not equal just to T. It's MC change in T to get to Q, so it's not. So A is the best answer, talking about overcoming intermolecular attractions. Now, of course, they said completely overcome. In truth, gases have some attractive force, so I'm not loving the answer entirely, but it's the only choice about intermolecular forces. And I can't say enough, party people, when I'm talking about melting, boiling, any phase change, we're not breaking bonds, do not talk about bonds broken. When I talk about why is the boiling point higher than this, you're going to get that question Monday. Somewhere, somehow, when they're asking you to discern between boiling points or melting points, do not mention bonds. You're talking about attractive forces. Although they didn't have a choice here, I needed to mention that. Okay? And now we have the lacrosse player hitting my wall here, because we're not doing anything important. Okay. 41.
I can tell you.
That's okay. It's
No,
not
no, no,
funny.
no. Let's hear her do it. Let's
Is
hear
it
her
bugging
do
you?
it.
Yes.
Okay.
Let's
Go
do
fight
it.
him.
I
wanna
two
witness it.
people?
I really want to.
No, no. Let's hear
Yeah, I
it.
wanna watch. I just
I
wanna
just wanna watch
I
this.
just want to witness it. I just want to watch you guys.
Alright, so I'm not gonna pause this.
Look at all them go.
Right now.
It's Akira. No, when men literally chased Akira, you're the only civilized.
Oh,
That's
true.
one.
Alright, so
Oh,
41, I'm gonna keep going
Alex.
since I'm rolling here. The enthalpy of vaporization of water is 40.17. Okay, you can tell people really want to be here. Which of the following best explains why the enthalpy of vaporization, I can speak, of methane is less than that of water? Why does it take less energy? Okay, think about it. The enthalpy of vaporization of water, that means the energy required to completely vaporize a mole of water is 40.7. Which of the following best explains why the enthalpy of vaporization of methane is less than water? Well, why would it be lower? Because it's easier to separate methane. Its intermolecular forces are not as strong, so it takes less energy. Now, what does methane, or what does water have that methane does not? Water has these electron deficient H's, otherwise called H bonding. Or as I like to say, H bonding. So, methane does not exhibit hydrogen bonding. Okay, but you say, Mr. Grodsky, methane has what, a carbon and 4 H's. I see an H here. Okay, so why wouldn't this H of one methane molecule get an H of another? Because this carbon's a hydrogen H is not electron deficient. It's got to be bonded to a FON, having FON with H bonding. Okay, this is essentially a nonpolar bond. Okay, so A is the best choice. All right, going on to 42. Okay, as you notice, we're seeing consistent type problems. You're seeing a PES question, a photon emission spectroscopy question. We're seeing questions usually with a mass spectrometer. We're seeing questions with, in this case, an alloy question. Or I'm thinking of another one that I can't think of off the top of my head that are coming up in almost every test. Okay? So here's an alloy question. And what you have to realize is in this question they're giving you some information, but the stuff to the left is the key. Notice we're making an alloy with iron. It's stainless steel. This is chromium, nice chrome wheels, okay? Especially the spinnies in Riverhead. Now, the point being is that we have iron and chromium both have the same what?
Cool.
Approximately the same molar mass. That's not the key on it. I mean to circle those, okay? They have approximately the same atomic radius. That's the key, not these guys. So when you put them in, this is going to be called a substitutional alloy, because chromium can take the place of where iron is. If I look at my choices, where is it where I have chromium getting in between because it's too small? Look at C. I'm going to get rid of C because chromium, okay, is about the same size of iron. It would take the place. It wouldn't go in between. So that's why C is gone already. Now, where would carbon go? Well, carbon, for the same reasons, is smaller, okay, in terms of what? Its atomic radius. So with the carbon, we make steel, we use carbon, and carbon goes in between the irons and or the chromiums because it can fit in there. We call this an interstitial alloy, but we're putting both of these together. And what the question is really reading is, which of the drawings is correct? If I have a scenario, and they're telling you this in the problem, the reason why it's called stainless steel is because it doesn't rust. The chromium atoms get oxidized by the oxygen and form a non-reactive layer of what? Chromium oxide. So that's the chromium metal with an oxygen. Oxide just means a salt on the top layer. And they say that this layer prevents the rusting. So the surface choice, the top layer choice, have to show chromiums and oxygen, okay? And notice oxygen is what? Very small radius. I keep doing the molecular mass. Has a very small radius that's very similar to the what? Radius of the carbon. So the oxygen will get in the crystal a little bit, but it's only going to be at the surface. It makes a protective layer. There's going to be no oxides inside the compound because the oxygen can't get there. So if you look at where else we have a nice possible answer, duh, D, here's chromiums, and here's the oxide layer, but having, okay, and that's a possibility, okay, but you notice on the inside, this right here, we're seeing oxides. So if you see the inside layer having oxides, that makes no sense because the oxygen can't get inside the metal. So C and T go bye-bye. And if you notice, A isn't showing any chromiums, okay, in the surface layer. So B is the best answer. Why? Because the O and the Cl take up spots in between. The top layer has that protective layer of chromium oxide. There's no oxides in between, okay? We have some carbons, and the carbons give the steel the strength. Why do the carbons give the steel the strength? Why is there more hardness in the steel? Look, here's my iron, okay? And here's my iron. And if I have an interstitial alloy, this has been popping up, and I'm not a great drawing, but if I have my my carbon being added in the middle, and I hammer down on this, even though I didn't draw it really well, okay, it's hard for this iron to be cleaved because it's going to hit this little guy in the middle. So it gives it hardness, okay? Any case, choice, whatever question that was, 42 was choice B, okay? Oh my gosh, so many people got this wrong, okay? So many people got this wrong. How many times are they going to ask you whether something is first or second order? They can only ask you that with graphs, okay? In the reference table, they give you two formulas that are integrated formulas. They give you the ln of A of some times 0, okay, minus the ln of A some 0 equal negative KT. Now, if you rearrange this and make this positive, this is how they give it to you. This is the first one they give you. So this is for first order. So if I rearrange this, ln of AT equals negative KT. I'm just going to add plus ln of A of both sides. A of 0. What do I have? Y equals mx plus b. This right here is the ln of A at some initial concentration, and any point along this point is some ln of A at some time period. Notice the slope is what? Negative, it's going down. Notice it's a what? Straight line. In your reference table, this is the first one they give you. That's why choice B is the answer first order. Now, if this curve was bending, okay, it would not be first order. That has to be a straight line. Now, what is the only other possibility? Sometimes they ask you to what? Draw this, if it's first order. If you knew it was first order, they ask you to draw it with the correct what? With the correct y-axis. This is a really easy problem. Sometimes they ask you to draw this. Now, if it was second order, okay, they'd be written like this. 1 over A of some time period minus 1 over concentration of A at some initial is equal to positive KT. When I rewrite this, it becomes 1 over AT equals KT plus, just doing some math here, plus, I can write it, 1 over A0. And what would this be? Y equals mx plus b. This is the second one they give you. So this is for second order. Notice the slope is what? Positive. So this would go look like this if it was second order, and my y-axis would be labeled 1 over A. You're going to see that. That's a point or two on this test. That's really simple. But this is first order because it's giving me a negative slope and it's linear. Okay? All right, so I think that's a pretty straightforward question. Because for some reason, they get all crazy when they see natural logs. They get all crazy with that formula, with the natural log. I think they get intimidated by so many of these questions, like, oh my gosh, there's a natural log of something, when that all it is just that y equals mx plus b. They give you that in your reference table. Okay? So really nothing to be intimidated about. The hardest question on this multiple choice I thought was the equilibrium one, where you had to times it by 2 and realize that. But again, practice, practice, practice. These are the same kind of questions. Okay, here we go with this. The equation represents a diagram that shows two profiles, path 1, path 2, 44. Which of the following most likely counts for the difference between the reaction path 1 and reaction path 2? Okay, now first of all, some basics here. Okay, this is a potential energy curve. Number 1, it's endothermic. We're starting low and we're going high. This is my delta H, the difference of where I start and where I finish. Who's tapping their foot? All right. Now, stop. Now, so my delta H is positive 50. Now, the difference between path 1 and path 2 depends upon usually a catalyst. A catalyst will start a whole series of steps, a brand new mechanism that wasn't there without it. So it's not about temperature, okay? This is measuring different, basically different heights or different barriers to start the reaction, or I should say different activation energies. This is the activation energy to overcome this barrier for the reaction to occur. And of course, this lowered path is the lowered activation energy. Now, activation energy is labeled E of A. Okay? Use that to your advantage if you see that. Now, so it's not about temperature, because at higher temperatures, okay, more energy is available. This will happen regardless. We're lowering the energy needed to start the reaction. So what accounts for the path? Well, we should realize that a catalyst, okay, provides a reaction pathway that's totally different, and the combined activation energies of all the individual steps are going to be lower. So the presence of a catalyst in path 2. Now, I like writing it like this. If there was a two-step mechanism, it might look like this. And you could just measure the individual activation energies and add them together, and it would be overall lower, except my drawing was not really drawn to scale that way. So understand that a catalyst starts a mechanism, and that mechanism means that the combined new steps creates a new set of reactions that is overall lowered. By the way, I always say to my first year chem students that this is the non-medicated hump, and this is the medicated, right? So this is the what? The medicated hump, or this is the unmedicated hump, uncatalyzed, unmedicated. If you got a hump, you should catalyze, you should medicate it, right? And this is the medicated hump. Okay, enough said.
Just imagine that.
You got a hump, get some medication. 45. Which of the following best describes the flow of heat when 1 mole of X2 decomposes? So what they're asking you, can you realize that this is the enthalpy, the difference of where you start? And by the way, if you didn't notice that, the potential energy of the what? Products minus the reactants gives you a positive value. That's what delta H comes from. So it's positive, it's endothermic. That means energy is what? Being taken from the environment. Now, why is it 50, not 100? 100 represents the activation energy of the catalyzed reaction. They're making you realize that delta H was 50. So 50 joules of heat are transferred into the surroundings. That'd be released. That'd be exothermic. 50 kilojoules are transferred from the surroundings. That means it came from the surroundings. It was consumed or absorbed. B is the answer. Okay, so not very difficult, but making you look at potential energy curves again. And here's another delta S question. I like this. You're going to see questions like this, 46 definitely. Okay, in 46, the reaction is thermodynamically favorable. Okay, now what does that mean? Delta G is equal to what? If it's thermodynamically favorable. You gotta get this down. Delta G is positive or negative? Negative, correct. Now we know delta H is what in this problem? Positive. Now let's check out my formula. Now you probably can see this right away. For me, I've got to do this. Delta G, which has to be negative, is equal to delta H minus T delta S. That's what delta, one of the ways delta G is equivalent to delta H. Now, this is definitely positive. Minus what? Well, this better be what? It better be positive. Why? Because by putting a positive here, and I do plus a negative, this must be positive enough, and because of the negative sign, does what? Makes this negative enough to overcome this positive delta H to make this negative. So it can't be equal to 0. It can't be equal to delta H because that would be 0. If this was 0, delta H would be delta G would be positive, right? If this whole expression was 0. If delta H was, if this was equal to delta H, then delta G would be what? Positive. So this value has to be greater than delta H. Some people say, what's this divided by 298K? We'll just print this T on the bottom, that's all. But the bottom line is, this value has to be big enough in entropy, positive, to overcome this bad enthalpy. Why is this bad? We're taking energy from the environment to go into a reaction. That is bad in terms of the second law of thermodynamics, because you're making the gas particles now go slower. But if the system in the reaction is increasing the entropy enough to overcome this bad event, then the process will work because the overall entropy of the universe increases. So any case, if you didn't like that, and some people still don't like that T, watch what I do here again. Solve for S, delta H, okay, minus delta S. And if you just think about it, this has to be a big enough positive. This is a positive value, okay? This has to make this be a big enough negative to make delta G negative and make it thermodynamically favorable. That's why C is the answer. Some point of that will be picked up. Okay. 47. Probably overtaught that again. Okay. Oh my gosh, we just did this? No. Looks very simple. Looks very similar. I can't speak. Too many. Review videos. 47. Which of the following diagrams best illustrates how a displacement of an ionic crystal results in a cleavage, which means a splitting, and brittleness? Okay. You guys know ionic compounds can be split, and the reason is right here. If you hammer down on a crystal that's ionic, you could put two negatives in close proximity. These guys are going to what? Repel and break apart. This, okay, is showing a scenario where we're adding different, all of a sudden we're adding positive 2 ions in here, we're doping this. Okay, so this is not showing cleavage, it's showing just the doping of ions. Don't be a dope. And C, this is a good one. C is showing metallic bonds. This is showing the reason why things that are metals or metallic or have malleability or ductility, they don't cleave or break as easily, is because when you hammer them, these electrons are so loosely held, they buffer the nuclei in the crystal. So C would be showing why they don't what? Break. This is showing ductility. So this question could be C if they're saying which of the following shows why metals are ductile, that don't cleave or not brittle, or the word are malleable. Okay, ductility just means you can draw them into wires because they are not going to break because of this, and malleability means you can hammer them and shape them any ways. But the best answer here is of course A, because brittleness is, and something else you should realize, an ionic crystal like sodium fluoride is positives and negatives equally interdispersed in a 3-dimensional crystal. A is the best choice, and D is showing molecular compounds that, okay, are attracted by London dispersion forces, okay, and they have a little bump here. Okay, 48. 6 mole sample of C3H8 and 20 mole sample of Cl2 are placed in a previously evacuated vessel. How many times have they talked about a previously evacuated vessel and they put in gas? They're in love with gases, okay? So you'll see a question. When they react according to the equation above, after one of the reactants has been totally consumed, how many moles of HCl have been produced? Okay, so this is Jeopardy. Now this is a limiting reagent problem. Okay, sorry, I'm just losing it. Actually, I have lost it. Okay, now, so I'm going to do an ice table, a stoich table. Okay, now, I'm going to kind of do it backwards. I've got 6 moles of this sample, and I got 20 moles. Now, what I do real quickly to figure out limiting reagents, I always keep it in moles. Now look at the ratio. It's 4 to what? 1. So I'm going to start with the one with the greatest number of moles. I'm going to lose all of that, because I know that this one's going to be what? 1/4. Right? The one with the greater number here, okay, this one has to be a fraction of that. That's one quick trick. This has to be 1/4. And we've seen that in another problem that we just did, what? I don't know, 20 questions ago. These questions are very similar. So, I'm going to get rid of, I'm going minus 20. So I'm doing initial, change, and then at the end I'm kind of doing a backwards ice because it's written this way. Now I'm not going to do minus here. This is not going to be minus 20. Because this is minus 4x, this is minus x. This is minus 20, this is minus what? 1/4 of 20. So this is minus 5. Right? Because it's 1/4. Right? It's a 4 and it's a 1. So this, after I subtract at the end, I'm left with 1 mole of this and 0. So this is my limiting reagent. It goes bye-bye. Now, why did I have to do that? I had to figure out who my limiting reagent was before I started the problem. Because if I picked C3H3 to do the stoichiometry problem, I would overestimate the product. Maybe you guys would have saw that faster than me doing this. Again, I'm showing you every piece of this. Okay, are placed in a previously evacuated vessel. Okay, now when they react according, after the reactants have been totally consumed, notice this is not equilibrium. It's called what? Completion, correct. We're going to drive it forward. How many moles of HCl have been produced? All right, well, I'm going to start with my limiting reagent, which is what? 20. And of course, look at the ratio. It's 4 to what? 4. So if I have 20 moles of my reactant, how many moles of my product? 20. But you could have done this, and they're very nice. Okay? But you had to figure out first who the limiting reagent. You couldn't assume. Is 48C? I can't believe they would do that. 6 mole sample, yeah, has to be. Okay? So they were very nice, so you didn't even have to consider the limiting reagent here, but I just feel like another problem, okay, they would have picked, they would have had the non-limiting reagent. Because so you picked 20 because it was 4 to 4, but what if in some scenario this wasn't the limiting reagent? You would have gotten it wrong. So you have to go with the limiting reagent, okay? Or you can go with how much actually reacts. Look at this. 5 actually reacts, and this is what? Right, okay? So that's why 48 is C. It's an easy question. I went over limiting reagent. You probably could have gotten by without it by luck, okay? Oh my gosh, here we go with boiling points. They love, at some point, for you to understand. This you better have down. If they ask in part 2 for boiling points, do not say it has stronger intermolecular forces. That's too vague. You have to explain. They want you to explain all the forces. I know this is a multiple choice question, but you could see these 3 on part 2 and explain. Like, consider this. So let's put this in order of lowest to highest boiling point. How am I going to do that? I'm going to identify the attractive forces. I see some O's here. This gives some polarity, doesn't it? So this not only has dispersion forces, LDFs, it's got dipolar forces. This is only hydrocarbons, which means I know that it's only nonpolar. So this only has LDFs. Now, why do they give me the molecular mass? There's a link to molecular mass. The link to the molecular mass is a link to essentially how many protons you have, which is linked to how many electrons. By giving you similar molecular masses, they're saying to you that you have similar number of electrons about, okay? So that's how it works. So they're telling you that all of these have similar LDF forces. And you should be explaining these, okay? So why is butane going to be the one that's lowest? Because it only has what? LDFs. Now what does acetone have? Acetone with itself has LDFs, but also has what? No, it has dipolar forces. What does that mean? It's got a negative end and probably a slight positive ends. This is a polar molecule attracting. It does not have any H's that are bonded to a what? FON. It does not have any electron deficient H's. So this has no what? H bonding. Now what does one propanol have? It's polar, so it's got dipolar forces, correct? But what does it have? The other two don't. Right, this H is electron deficient, so this one has LDFs, dipolar, and H bonding. So if you were to tell me, list these in increasing boiling points, you would say butane. Who else? Acetone, because it's got less forces. And then the one with the highest is the one that's all three, 1-propanol. And if they ask you the differences, tell them, talk about the other ones. Propanol, it's not so much that propanol H bonds is the only reason. It's that propanol has more attractive forces, has an additional attractive force, correct. And I'm telling you, you're going to see that, okay? And so the question answer here is B, okay? And last one in the multiple choice, okay? And my gosh, a real easy question. They give you a lot of information. The reaction represented above occurs in a single step. Okay, because I know that, the coefficients become the orders. Okay, but that doesn't help me. Okay, between the particle of NO and NO2. We would call this, my friends, a bimolecular collision, right? Two of these collide. When one thing breaks apart, it's unimolecular. So sometimes you'll hear that word. Anyway, a scientist, oh my gosh, correctly calculates the rate of collisions between them two and has sufficient energy to overcome the activation energy. They're telling you that it's occurring. The observed reaction rate is only a small fraction of the calculated collision rate. So we have enough activation energy, yet it's barely going. So what must explain the discrepancy? Well, this is called collision theory, something you learned last year. In order for a reaction to go, you must have an effective collision. What's an effective collision? The first priority is you have to have high kinetic energy, which means high energy has to be given so that the colliding molecules overcome their repulsive forces, which is the cloud of electrons. This is activation energy. You must have high enough energy to slam to either break bonds or create them. That's activation energy. And the second one people forget, and that's what this question is, especially for big molecules, is you have to have proper orientation. Why is that? Well, in big molecules, there are going to be places where bonds can be broken and where they can't be broken. Case in point, you guys learned about pi bonding. In a hydrocarbon, where you've got this double bond occurring, single bond between, let's say, a hybridized orbital, and then you've got the what? The pi bond occurring here, above and below. Pi bonds are easily broken because they're a little farther away from the nucleus. A particle that's going to bond with this carbon has to hit this pi bond. If it doesn't, it's not going to react. So I always call proper orientation kind of like my family at a reunion. We're not good dancers, and the chance of an elbow-to-elbow collision is slow. So the elbow-to-elbow collision would give you the proper orientation. So, any case, the answer to this question is, which of the following explains why, even though we have enough kinetic energy or activation energy, they must collide with the proper orientation. They have to hit their active sites. Okay, that's why B is the answer. All right? So, we're done with this multiple choice. I will post it with the second half. I will link it because I have nothing else to do in my life. All right? But that shows you the second part. For those that weren't here yesterday, the 1 through 25 is also posted, and I'll put this all together.